Okay, it's slowly setting up. It's a good bet that we didn't live stream on YouTube this morning, but we can convert the videos that we had. Okay, well, there is a delay there, so I'm going to close this out now and get back into Zoom. So anyway, so the meetings, the presentations this morning were recorded on Zoom, so we'll convert those over into YouTube recordings later. So we have everything there. So, okay, welcome back. It's about 1:30 now. We're going to start off the afternoon section of today with Jeff Baldwin with his At the Focus Hartmann test. And let me get that up on screen here. And he'll take it over. Okay. Let's get rid of this. Let's bring this down here. I wish I could figure out how to get rid of this, but oh well. Okay.
Would you guys prefer this view, or would you rather me put it onto slideshow view?
Slideshow. Well, if you can make that bar go away, slideshow view.
Yeah, well,
Something that makes it go away. Run more.
let's start with the slideshow view.
Make it relax. No, not that.
Beginning. And then, okay, I don't know how to move that. I'm gonna let you move that.
I think we can just grab it,
Oh, very good.
push it up there.
There's something under more that allows you to move it, or what am I? No, we did it. I could do that.
Well, if you keep the cursor off the screen, it'll stay like this, but when you move the cursor back on, it comes back down.
Okay. Go
So-
touch the mouse.
Okay, we good to go?
Yeah.
Okay, howdy, I'm Baldwin, and I came with Lonnie and Bill. First of all, thank you, Dan, for letting us do this. Thank you, Howard, for letting us come in here, and anybody else who had anything to do with this, thank you very much.
Gary and Marion.
Gary and Marion, thank you. Okay, they're around here somewhere? I don't see them.
Well,
Okay.
Gary is, but Gary is.
Okay, so thank you for having us. I was a caustic tester, of course, Foucault tester back in the day, and wire tester. I was a caustic tester, and I would spend hours setting up my jig so that was on axis, both vertically and horizontally, and that would take forever. But then I'd start the test, and on a caustic test, you come out to your outer zone, you find your two dots, you measure them across, and you finally get that settled in. Then I have some strings that flip down the flaps and pull up the next flaps, move it in, measure the next dots, move it in, measure the next dots. And Schrader on the ATM manuals has a fixed light source moving test stand. I rewrote my caustic so it was both moving. So my arithmetic was different by a factor of 2 for that. And it was a pretty good write-up that I did. And it would take me about an hour to get all the way in. But then I'd come out to the outside and the numbers would be different. So I'd have to start it all over again. I'd come out to the outside, the numbers would be different. So it would take me all day to set it up. And then I'd start testing about 10 o'clock at night. And in California, the garage gets cooler and cooler and cooler. And I realized what was happening is over 20 feet and measuring to a 10,000th of an inch. As the garage cooled, the floor shrank and my test stand and mirror were getting closer to each other, throwing the numbers off. Until about 4 o'clock in the morning, everything came to a stop. I'd get a good test. Insane to work 3 mirrors on a mirror and then all night long on a test. So Bill and Lonnie showed up one day and said, "Hey, you really need to do our sit test." I go, "I know what I'm doing. Get away, shoe fly, arrogant little egotistical dog." They came back, thank goodness. And I pulled my head out of my can and I saw Bill's sit test in action. And I was an instantaneous believer. It was more accurate than the caustic test. It was very repeatable. and it was so fast. I mean, you have to let your mirror acclimatize and your shop acclimatize, but when you actually do the test, literally 3 minutes of your time and maybe 10 minutes on the computer. And it's repeatable and accurate. So I was an instant believer. My issue came along where I needed multiple radials on my test rather than a single axis. I needed multiple radials. And Lonnie came up with the Easy Hartmann test, and that solved that problem. And so I started doing the Easy Hartmann test and still do the Easy Hartmann test. And if you look at the jig, people out there at Zoom land, sorry, I'm going to point to something that you can't see here. But I'll try to stand my body out of the way. Right here is where you're receiving the information from the mirror down there. Right here is the light source. So right and left, you're on axis. Up and down, you're off axis by about that far. And so we haven't seen a problem with that, but theoretically, there's a problem with that. So I thought if I could do an on-axis at the focus Hartmann test, I could confirm or deny whether there is actually a problem there. And so that was one of the reasons I went to the at the focus Hartmann test. One of the reasons is it's at the focus rather than the ROC. So all your dots should be conjoining at one place rather than a pattern when you're at focus. And that may or may not be an issue at all. It's on axis. The other thing is when you're in the shop, you've got your optic and your optical axis is horizontal, and then you put in your telescope and all of a sudden it's up in the sky. I thought, well, if I start up at the sky, then the gravity factors and stress and strain aren't going to change going from here to here. It'll be what you get, it's what you get. And so I wanted to be at an observing angle when I did the test. It's also testing the whole system. It's not just your primary mirror, it's your how it's sitting in the cell, it's your secondary mirror, it's your collimation, everything. The entire system's being tested in one shot, and that's also beneficial. I wanted to do this as a sanity check to see if his test, Mel's test, everybody's tests are all collaborating with each other. And also to check to see if this off-axis, vertical off-axis nature on the Easy Hartmann test had any issue whatsoever. A person might say, well, why don't you just star test? Well, this is like a quantitative star test. It is a star test, only instead of saying, I got a high zone at 40% or I have this, I can actually go and say, range 6, zone 3 has a high spot. I can actually locate and identify a particular spot. I think it could be used on any optical system. I should be able to do it on a Cassegrain, a Schmidt Cassegrain, a refractor, a Newtonian, literally any kind of telescope, because the wavefront coming from the sky planar, coming off the optic, whichever kind of optic it is, they need to be spheres coming down to your focus and then leaving as spheres. And whether it comes from a Ritchie-Schraden or a Newtonian or refractor, that should be the same. So it should work on any kind of optical system. I'm going to show you in a minute how I get off radial information error. And this test has to work for f2.61 to 3.6. That's my range of optics. I limit it at 2.61 because if you have an f2.61 and use a SIPS coma corrector, that brings you up to f3. And then with a 21 millimeter ear source, you got your 7 millimeter exit pupil. So I have no intention of going faster than 2.61. And I don't like making slow mirror, so I have no intention of going beyond 3.6. So most of my stuff is f3. Before I change slides, anybody got anything they want to throw in or correct me on or ask? Yes, Ron.
Just throw in the test itself is probably agnostic to F number for any F number.
I agree.
Right.
But I have found a problem.
Okay.
And I'll talk about later, but like an F8 doesn't spread very far. So you have to go really far in and out. And an F3 goes really fast. And so now your sensor size is a problem. So there is focal ratio issues, but they're all resolvable.
Yeah.
Yep.
Okay.
All righty. So before I do an at the focus Hartmann test, I either lit test with Bill's test or Easy Hartmann test with Lonnie's test. I razor test for smoothness. I do turn down edge test. I make sure the mirror is finished and rated to silver before I go to the energy at the focus Hartmann test. It's a little bit of a pain, and you're out at night with your scope, and you have to acclimatize and adjust. So the last thing you want to do is work a mirror from a sphere to a paraboloid using this test. That would be insane. You want to do all your shop tests and get the mirror finished before moving on to this final check thing. So you can't have turned down edge. It has to be smooth. It has to be good on all axes, and it's ready to be illuminized. And then you go ahead and move on to placing it into the telescope. So this is a rough process. The mirror is basically done. Excuse me. You must acclimatize like you've never acclimatized before, because when we're in the shop, Lonnie was talking about fanning the mirror. So when I'm doing a test in the shop, I have a big sonotube tube coming in front of my mirror. The mirror is supported well with, I consider, highly engineered support, with an inch behind the mirror. There's a fan behind it, and there's a cover in front of the sonotube and a fan in front of it, and it just trickle flows mirror air, blows around the front, around the sides, along the back, and out the back. And I have to sit there for at least an hour and a half, because this easy Hartmann test is so sensitive that if you don't do that, you will get a difference in readings. Little, but they'll exist. So there's a big process for acclimatizing a mirror in the shop. Now you drag it out in your driveway and all that goes to heck on you, because you're at the mercy of God's weather out there. And so acclimatization is a serious problem. Another one that is really something you have to pay attention to is collimation. I have 3 versions of this test, and one version is where the mask acts as the mask acts as one set of data points and the sensor acts as another. And so, okay, so as the light comes down off the mask onto the mirror, the mask placement is absolutely critical if I'm going to do arithmetic with those numbers. I have an XYZ on the mirror, an XYZ on the sensor. And if my mask is to the right a millimeter, it's game over. So you're, at least on the single photo version of my test, it's critical that the mask alignment is there. So I focus the telescope with a camera. So I'll pretend that right now I'm talking about the 2 image inside and outside of focus here. So you would focus the telescope on the camera, maybe even with a Bratanoff mask, get a really nice focus, and then zero out your DRO or zero out your dial indicator. Then you can roll in, say 1.000 inches, take your photo, roll out 1.000 inches, take your photo. You now have your 2 photos inside and outside of focus. And then you would, I shoot in RAW. I would then convert it to TIFF, put it on image J, run all the arithmetic like Lonnie and Bill are doing, then put it into my spreadsheet. And my displays, I have 2 displays. One of them is, okay, so like here's the optical axis. I could place an orthonormal plane anywhere I want in there and see where the dots are hitting it. And then I can move it around and see those dots converging. So one of my displays is the dot package. The other display is, I copied this from Lonnie. It's an astigmatism check. So like on zone 7, that's my outside zone. I'll take those 2 dots and measure how many pixels apart they are, how many pixels apart those are, how many pixels apart those are, and how many pixels apart those are. I'll take the highest number minus the lowest number, and then divide that difference by how far apart they are. So it'll be like 2 pixels divided by 2,500 pixels. And then I'll get this ratio of astigmatic ratio by pixels by diameter. And the real question is, at what point do we say it's no longer any good? So originally we were doing the easy Hartmann test with this, saying let's not have any more than 6 pixels. But if you have a different sensor size or different pixels per inch or a different focal ratio or different distance back, that difference in pixels changes. And so it needs to be more of a ratio thing. Okay, so I could put my intercepting plane here and look at the dots. And those dots need to be straight, evenly spaced, and all pointing in the center. And if they're not, I can determine where to work the mirror to make them straight, evenly spaced, and pointing center. Once I'm happy with that, I can move my plane in, reshoot it, and then redo it. So, it's just like star testing. The closer into the focus you get, the more anomalies you can easily see. And so as I move these guys in, these dots quit being nice and square, nice and patterned for me. So, and then my display auto sizes to whatever the biggest thing. So if the dots are spread out, it'll auto size to that. I'm moving closer, the dot gets smaller, it just auto sizes to that. And after a while, I have this airy disk drawn in. And after a while, they get so close that the airy disk gets bigger and bigger and bigger. And the goal, of course, is to get them all inside that airy disk. I'm making no claim that if they're all in the airy disk, you have any such Struhl ratio. I'm not making that claim at all. But it's a nice target to aim for. Okay. I hit the button, nothing happened. I hit the button and nothing happened. Let's hit that button and Dad.
Meeting problem. Let's just try that. Okay.
Thanks, Rob.
Try clicking your mouse and see if that advances.
I don't want to advance yet.
Not yet. Yeah.
Okay. The buttons here are now working again. Okay, so there are 8 things to avoid when you're putting this mask on, because most of us have spider vanes, a focuser, and usually 3 mirror clips. And that outside zone 7 hole will hit those mirror clips, and sometimes the focuser protrudes in there. So I tilt my mask 22.5 degrees because usually spider vanes are up and down, right and left, or they're 45 degrees from that. And if you look at this mask, we got up and down and the 45s.
Mm-hmm.
So I go 22.5 degrees on my mask. So if I want to match with Lonnie's numbers, I then would rotate his mirror 22.5 degrees so that the mask locations match the mirror. Yes, sir.
So you're saying the mask needs to be rotated, not tilted.
Yeah, I'm sorry. Did I say tilted?
That's on your slide.
My bad. Oh, yeah. Okay, I'm kind of illiterate. Yes, we are going to rotate about the optical axis 22.5 degrees. And then if that runs into a spider clip, I might have to go back and forth a little bit just to settle it out. But there are 8 things that get in the way. And it wrecks everything when they do. By the way, there are 57 holes on this mask. There are 8 rows of 7, makes 56, plus a center hole is 57. I only make fast mirrors. So my secondary mirrors are huge. So there's no 0, there's no 1, and there's no 2. So that's 8 rows of 5, which is 40 holes. And so they would be zones 3, 4, 5, 6, and 7. And the middle of the mirror is not tested because secondary mirror is in the way. Okay, so there's no parallax problem. If you look at how Lonnie and Bill's test sits on the mirror, when the light comes from the test stand through the hole, it's going up and it hits the mirrors at a point not equal in radius from the center as the hole. And so there was a parallax difference. Mine doesn't have that because this is in the front of the telescope. The planar light wave comes down, hits the parabolic mirror, and makes spherical waveforms coming back. And the XY position for those places on the mirror equals the XY position for the holes in this. Yes, sir.
You might mention to the Zoom folks that you're holding up the mask.
I'm holding up a mask showing people as I'm talking. That must sound really stupid to them. So anyway, there's no parallax problem on that. But I do get an XYZ position. The XY positions are the same for the mask and the mirror. The Z position would be from the focus plus whatever sagittal depth there is at that hole. Then the XYZ positions on my sensor would be the other set of points. So if I use version 1, it's one photograph and one set of coordinates, the mask spot, the other set of coordinates is the sensor, and I'm making linear equations between associated dots that I'm intercepting with that plane and examining the dots. And there's a problem with this, and I'll explain that later. It turns out that 2 shots are better. Now, theoretically, if I can make a perfect optic and all this is working good, I should be able to then do the test with coma correctors and see if there is spherical aberrations by different brands of coma correctors. Should be able to do this with Barlow lenses. I should be able to do this with telecompressors. I should be able to examine different makes, models, and stuff to see if not only are they doing their job, but are they also changing the prescription of the mirror? I've heard some people say that SIPS coma correctors may make the mirror a little bit overcorrected. So that's one of my goals, is to find that out analytically this way. Okay, let's keep going here. Did it move? It did move. Okay. Okay, so I have 3 versions of this test. The first one I wanted because I wanted to just take 1 shot and be able to live with it. If I did a 2-shot inside and outside of focus, the problem is that most of the telescopes I'm going to do will be Newtonian telescopes set up for observational use. So the eyepiece focuses. If you take that off and put a camera on, it doesn't come to focus, let alone beyond the focus. So I'm out of business with that, unless I buy one of those guiding cameras that slide down inside there. And so I don't have one. I borrowed one for this experiment here. But the single exposure outside, I'm running into some issues. I'm going to get to those issues. Version 2 is, I didn't want to get a camera down inside my focus. I was just dead set to use my single lens reflex digital camera. So it is taking a picture outside, racking it out, take another picture outside, then using these 2 sets of dots to make my linear equation come down the focus. The other thing that's great about that is I'm having problems with the single shot. And I think part of the problems is the mask positioning imperfection is causing my linear equations to be incorrect. The nice thing about 2 shots is you've got thousandth of a pixel precision on one frame, thousandth of a pixel precision on another, and your linear equations are dead nuts on. They're just super duper. And so the third version, of course, is inside of focus and outside of focus. And with the Newtonians I've been using a really small, really teeny tiny little sensor camera inside and outside of focus. I'm having troubles with that. So I did it another way. You'll see here later on. That's the true Hartmann test, by the way, inside of focus and outside of focus. On a star in the telescope. Yeah. All right. So here is one of my images. And this is after it's been processed, because when you first look at a Hartmann image, the star has a dot in the middle, and it's like a planetary nebula. It's a little disk with a little dot in the center. It's kind of cute. But you needed to get the background jet black. So I process it so the background is jet black and the dots as small as possible. Notice there are only 40 dots. Notice there's a tilt. So in order to resolve that, when you move the camera in and camera out, they may actually be slightly different tilted, or they might be a bump and a transition issue. So the first thing I do on my spreadsheet is I'm going to use my mouse here, hole number 1 and hole number 10. I do an inverse tan to see what that angle is. Then I rotate the entire frame negative that angle. It squares up holes 1 and 10, and everybody else goes where they go. I then take my second shot and do exactly the same thing. So now I have 2 pictures that are oriented level with each other, but they may have a translation problem. So the next thing I do is I take the average of all the dots and I relocate it to a center on both photographs. Now the rotation and translation are set up, and I can run my linear equations. I don't think I'm jumbling anything up doing that, because the results are quite good. Notice a big hole in the middle where there's no information. Who cares? It's behind the secondary mirror.
Your upper right dot is blue. What's going on there?
That is, okay. On this particular photograph, I used the wrong size of mask on the wrong optic, And so that's hole 7. And so I haven't eliminated it. So it was peeking through a little bit on one side and not on the other. So if you're looking here, right there's hole 7. I'm using 6, 5, 4, 3, and 2 on this particular mirror. That's not the case on all the mirrors. It's just the particular one I did was
Well, I
like
think
that.
my question was why did that happen? Was it a mask not aligning with the mirror or something else?
It's not perfectly aligned. And lucky for me, on this version, it doesn't have to be perfectly aligned. On the single shot, it has to be perfect. But on the 2 shots, it doesn't. Yeah.
So the very bottom center, with the halo around it, the blue and some green,
Not sure what that is.
and then up at the top it doesn't, so.
I'm not sure what that down there is. Honestly, I don't know. Yeah.
Neither do I.
I don't know if it's remnant of the process or the remnant of the funny stuff I've been doing to this thing. I don't know.
What were
The
you centered on when you took this image, Polaris?
I always use Polaris. It's easy, it doesn't move. In my home, it's 37.5 degrees high. One of the reasons I'm doing that is if I'm going to observe from 20 to 70 degrees, I might as well check optics somewhere in the middle at 37.5 and possibly alter my optics until they are suitable at that angle, rather than doing it at 0 degrees and going to 20 to 70. That's one of my logics. Whether it's sound or not, I honestly don't know.
Obviously, that's why you moved to that latitude.
Well, actually, that Mel was talking about 17 degrees out there. That's why I moved to that latitude. Lots of reasons. I did live up here. I live down there now. All right. So again, just like the other 2 guys, I'm using ImageJ. So there's an ImageJ program at the top. And there I am circling one of my dots with the circling thing. So Lonnie and I goofed around with this image and we worked it out so it's really black. And then I moved the dot around and the center of gravity stayed within 1,000th of a pixel. If it moves a few thousandths of a pixel, it's probably okay, but it was stationary to 1,000th of a pixel. If you look at this one here, that one on the bottom no longer seems to have that blue thing next to it. Am I correct?
It doesn't have the green thing. Or is that the green thing? Or is that?
You know, it's funny. I don't think this is it, but Polaris is a double star and they are different colors.
Yeah, that's right.
I have no clue if that's got anything to do with nothing.
That's a really good question, actually.
But you'd think it'd be popping in on all of them. I'm gonna move forward now. I'm afraid of your question, so I'm just gonna keep going here. So that's what my spreadsheet looks like. The top right display is the dot pattern at some point inside of focus. When I say inside of focus, I'm referring to the mirror side of focus. And the chart on the bottom is my astigmatism analysis. So I'm going to start there. On zone 7s, I look at how many pixels apart the opposing sides are. Then I take the big one minus the small one and I stick it right here. And then I take that number and just divide it by whichever is top of the list. They're also close. It doesn't matter which one I do. And I get this 0.0019. So on the scale I made, I consider that good. I'm going to have to change that around because I don't know at what point it becomes a problem.
So that's 0.2%.
Yeah.
Right?
Yeah.
Okay. That sounds like a very small number,
But
that's not a wave rating either.
it isn't.
So what does it mean? We don't know, but okay.
I'm making no claims at all about Struhl or wave ratio or nothing. I'm just trying to see what happens when they conglomerate into a point here. So what I need to do, that's just for picture number 1. I need to do picture number 1 and picture number 2 and see if they match. That's the first thing I need to do. The second thing I need to do is visually see when astigmatism a problem and connect it with a ratio. And I haven't done that experiment yet. And I plan on posting on Oregon Scopeworks my progress on this and my failures. So I will hopefully get to you on that. All righty, I'm going to just keep clicking here. So once you've got your spreadsheet up, all the yellow fields are the one that you put stuff in. The spreadsheet auto levels both arrays, it centers both arrays, creates linear equation between associated dots in the two photographs, and then it intercepts it with that plane that's orthonormal to the optical axis, and then plots dots based on where I select the intercepted plane, and it also puts in an airy disk. Now, the airy disk is just a size scale for me to look at. I'm making no claims about Struhl ratio at all. I just needed something on there that says it's this big. And then it calculates the astigmatisms for each zone. So I took mathematically perfect numbers and I put it in my spreadsheet as a spreadsheet test. And so whichever one is bigger, the array of dots or the airy disk, the graph auto fills to that size. So all of my dots right there, that is all 40 dots right there, coincident with each other. And of course, the airy disk got really big. So that showed me that that part of it's working. Then my astigmatism checks all came up 0.0000. So I'm fairly confident with my spreadsheet. So I went out and checked a couple of Dobsonians, thinking the really good one was going to give me something like that, and the bad one was going to give me something like that. So over here is one of Lonnie's mirrors, and it is a pristine mirror. And over here is my friend Mike's. He has a mid-80s Coulter Dobsonian 17.5 inch, never been refigured or reluminized. I tested it and it's about 1.42 waves and astigmatic. So I expected this for Lonnie's and this for Mike's. Well, on the single exposure test, they both came up equally crappy.
Thank you, I appreciate it.
Yeah. So there's no way I could evaluate a mirror under these conditions. So again, I have issues with the single image version. It's at this moment unreliable. So problems could be mask position, acclimatization, because when I did both of these telescopes, I just went out in the driveway and shot it. I didn't let it acclimatize at all. The collimation was imperfect. We don't know about the secondary mirrors, and they're both under light polluted, hazy skies. And so you get all that bright stuff inside that encircling thing. It moved that dot around all over. So these two shots really pointed out that I'm failing badly. So I went on to the 2-shot versions of this. I am going to come back and readdress the single shot. I'm going to tell you, I have zero faith I'm ever going to get that to work. But, I'm going to try. Okay, so I took what I considered my best personal telescope. That's an Astrophysics Starfire 140. And I did, on the left side is my inside of focus, outside of focus version. And on the right side is my 2 outside of focus versions. They were shot on different nights. And I will say there wasn't a lot of acclimatizing going on, but I was able to get all of the dots inside the airy disk on the inside outside version. However, look at these astigmatisms. They seem to actually be kind of undesirable. It is possible that I need to check my code, my spreadsheet coding on there. Maybe there's an issue, I don't know. Then on the both outside of focus, I have a few stray dots. What I did was I compacted them to the smallest I can get it. And that's as good as I can get for the 2-shotter. So the actual Hartmann test inside of focus and outside focus is still superior to the 2 outside of focus. But it could be me, not the test. But this guy right here, that tells me my spreadsheet's working because I took a very good telescope and it gave me very good results. So I have a little faith in it. Okay, so let's go inside of focus a ways. And those dots are not straight lines, evenly spaced, nor are they pointing to the center. And so what I would do at this point is work the mirror until they are, and then move to a closer spot, and then work the mirror until they are, then move into a closer spot, work the mirror until they are. Of course, before I do that, I would maybe take 3 Hartmann tests on 3 different nights, because maybe that dot right there will be here tomorrow night and over here the next night. So if the dot's moving around, it's not a good dot. If the dot stays over there, it's probably a good dot. So here's a cool thing I like about it. On Lon and Bill's test, you can tell if your radial is undercorrected or if your radial is overcorrected, but it's on the radial. On my test, the dot can move over to the side, which means the error is actually off the radial. So I can now go in between the radials with this test. So when I'm inside of focus, you can imagine that the wavefront, let's pretend a perfect wavefront is flat. And if it's undercorrected, it's a bump. So if I'm inside of focus, the dots will run downhill off of that bump. So that means that this dot here is because there's a high spot off the radial over here. I'm going to go to another image here. Here's another one. Look at zone 7 and zone 6. Look at that big gap in there. That means there's some kind of hill between zone 7 and zone 6. So that would be an undercorrected zone. And over here, you see how short those guys are and how long those guys are? I think that's a collimation problem because I'm obviously skewing it over to a chromatic appearance. So there's a lot you can tell from this Hartmann dot array. I like the fact that you can tell if you're overcorrected or undercorrected by a zone. I can tell if I'm on a radial or off of a radial. I can tell if I'm not collimating. Yes, sir.
How long are you exposed to?
Okay, I have been experimenting with that, and I am doing 30 seconds at ISO 800, and it's focal ratio changeable. So I think on Lonnie's mirror, when I did 30 seconds at ISO 800, I got a lot of background stuff I could not eliminate.
The reason I asked is in adaptive optics, they have a Hartmann wavefront sensor. And it's optically exactly what you're doing.
Really?
And what it is intended to do is show the distortion in the atmosphere. And so in a short exposure, you will see the tilt of the wavefront. And on a big mirror, assume the cell in the atmosphere is on the order of a few centimeters. Maybe 10 centimeters, but if you're at sea level, it's probably not 10 centimeters. So if you take a short exposure, I suspect those things will bounce around quite a bit. 30 seconds.
30 seconds gives me a very good averaging. We do the same thing in the Easy Hartmann shop test, where sometimes that air is moving just a little bit on there. You take a 30-second exposure, it averages out, right, and it becomes unbelievably repeatable. I haven't tested this yet for repeatability.
30 seconds should be okay.
Yeah.
But if you'd said it was the 30th of a second, I would have been.
Well, this image here, I would definitely not work a mirror because I could tell it's off axis. So forget working the mirror based on anything I'm seeing here. Will its off axis nature cause that dot to come over and that dot to go back? Probably not, but it's so obviously off axis that it would be crazy to work a mirror based on that image. That's my feeling, at least. Okay, so here's another one. And would you agree that you can't tell what dot came from what zone, range, anything? So you have to start far from the focus and work the mirror there, then work in closer, work the mirror there, and work in closer, work the mirror there. The goal being that all the dots are going to end up inside the circle. That's kind of the ticket there. So dot misplacement indicates error and therefore correction. By the way, I'm not going to tell anybody how to correct a mirror. We all have different ways to correct a mirror, but there are two basic logics. If a dot has moved, it's because the slope is wrong, so you can alter the slope there, or because there's a hill next to it, and you can wear the hill down there. So you can either be a wear the hill down guy, or you can be the alter the slope kind of guy. They should both work. I like this because it can look between radials, where Lonnie's test doesn't look between radials. This test will look between radials. So I don't need 16 radials. 8 will do, I think. The dots like to fall downhill when I'm inside of focus. They will climb uphill if I'm outside of focus. And I can keep zooming in until I get it the way I like it. So I'm pretending to be Dale Eason on this picture here. By the way, Rob was talking a little while ago about Excel spreadsheets, kind of like the poor man's, way of programming. I can't program nothing. I can't even do a spreadsheet for garbage here. So I kind of got this thing working. It's working okay. But as far as graphics go, I am not the guy. And I don't need graphics to do it. I could just look at the dots and I'm going to know what to do. But in case you want a picture, I could have had a third grader draw it, probably would have been better. But if you look at how big this gap is, there's obviously a high spot in there. And it's really easy to think the high spot is here, but it isn't. It's way out here because this dot and this dot are actually closer together and the gap between them is way out here. So I would draw this thing here telling me where my hills are. Then I come back to the original map of the mask and properly place where those hills are. Now, if I'm a wear away kind of guy, I'd wear away those hills. And if I'm a change the slope guy, I would do it differently. And I'm not going to pretend to tell anybody how to correct a mirror, but the information is there to correct the mirror. Okay, so I have this huge area in the center that's not covered on the test. And like I said, I only do large aperture fast focal ratio mirrors. I got this huge secondary mirror. So I don't need zone 0, 1, and 2. But it would be nice to know how the transition of the correction goes from zone 3 into the secondary obstruction. And it'd be nice to know how the correction goes from zone 7 to the edge of the mirror. So I not only will do the Hartmann test, Lonnie's Hartmann test, Bill's test, and my Hartmann test, but I would also check the center, possibly with a bath interferometer, because the center of the mirror is very slow. And my bath, I don't have problems with slow mirror bathing. A knife edge to see if the entire thing is smooth. And on the edge, I do a double pass interferogram against a reference flat. And I look at that point, the interference fringes are straight. And you can look at how they go off the edge of the mirror to determine how far in an edge is bad and how far it tweaks over. So to me, that's how I like to analytically determine the edge of a mirror. Of course, there are many other ways of doing that, but those are the tests I do in addition to our Hartmann testing. So I think that's what this thing is. I check for turn down edge, check the central region, check for smoothness, all this other stuff. Sanity checking is always good. Doing your own test and relying only on your own test isn't safe. Okay, so I'm going to go back now to my original single image failure. And I think I already listed all this, so I won't bore you with that again. But I don't plan on doing the single image version of this probably ever. I don't know. I really had hopes for it because it's easy. And when something's easy, it's usually not the right way to do it. Okay, so I'm going to look at some collimation pictures. This was shot with one of those little microscopic guiding cameras down inside a telescope. And this was my, I can't remember whose telescope this was now. So you want the guy on the left. And the guy on the right, your collimation stinks. And if you tried to Hartmann test with that, you're going to have failure. So you take the guy on the right, you adjust it till it looks like the guy on the left. Then you jack a higher power eyepiece on there so you can look at the same thing only closer to focus. And you do it again. And you stick a Barlow or two and you just keep going until you can't go anymore. And it's really important that you keep going before your Hartmann test, because if you were to do a Hartmann test with that image on the right, you can see how scrunched up the 1 o'clock line would be and how spread out the 8 o'clock line would be. So it'd be useless information to you. And so if you go ahead and collimate it, say with a 20 millimeter eyepiece and get the guy on the left, you're still not there. You're so far from the focus that isn't good enough collimation. So put a 3 millimeter eyepiece and a Barlow or two on there and get it like the guy on the left, is powerful as you can get it, and acclimatize before doing the test. So like Lonnie, I marked the back of my mirror with my zone. So I polished both sides of the mirror. If anybody's interested in why JP Astrocraft and Mike Lockford talk about mirror cells and polishing the backs of mirrors. So this is actually a 22-inch mirror flipped face down on that paper towel. I take the mask, I lay it on the back of the mirror, and I draw all the circles on there. Then I put it back on my machine, optic side up, and I can see right through my mirror at the zones and ranges. And now that I know what zones I want to work, I can go directly to it using that mapping process. And as I rub it, it's not on the surface, so it doesn't get in the serum and it doesn't wipe off. So that's how I will target errors that I have found on both the easy Hartmann test and the focus Hartmann test. All righty. The changes I'm going to make, I'm going to color code my dots. So zone 7, I'm going to make blue. Zone 6 will be dark green. Zone 5 will be green. Zone 4 will be yellow. And zone 3 will be orange. And then, of course, the area disk will be red. That way, when all those dots come together and they're all in a bundle, you can't tell who came from where. At least they'll be color coded. I'm going to add on here a second astigmatism chart because there's 2. I'm going to add sliders. So when I move my plane, instead of punching a number in and hitting enter, I'm going to add a slider so it'll move it. I'm going to take the data and make 8 millilacroix graphs, and I'm going to use Euler's method and come up with some profiles based on zone 7 and based on zone 6. And who knows what other changes I'll make. But that's my Hartmann test. There's my email addresses. If anybody ever wants me to send them a copy of it, I'll send it. And then when I have updates to it, I'll send out the updates. Howard.
Yes. I'm really impressed. Although I'm confused in how you can determine whatever astigmatism you find is in the mirror or in the cell or in the back.
First of all, we find 99% astigmatism tested with his test. On his test, this astigmatism test keeps you from moving any further on a mirror until they are all gone. And so I'm kind of assuming that once it goes in the scope, it is astigmatic free. However, the cell itself could cause it. So I'm looking at this numbers here, and I'm not at a point now where I can say, I trust my astigmatism chart. Give me another year and maybe I will trust my astigmatism chart. At this moment, I can also say from my test, I'm trusting the chart. His test, I trust it completely.
So you have an independent astigmatism measurement for your mirror,
Yes.
and that's good. And you have a system level test, which is wonderful. And earlier you talked, I asked you about that ratio, right?
Yeah.
You're going from end to end. You take all of your outer points, all your zone 7s, and you get this ratio.
Yeah.
And I was looking as you presented, and I didn't see what I was hoping to see.
What was that?
Get the ratio for the endpoints of each of you got 4 axes, right?
Mhm.
It's the change in those ratios that is going to indicate your astigmatism. It still has a ratio.
Mhm.
Right now, you just got a number. You don't know where the astigmatic axis is.
I do.
Oh,
I'll show you.
show me.
Sorry about that. I was going a little too quick through that slide there, but here we go. Axis 1, axis 2, axis 3, axis 4. That green guy there, 2783, that's the long one. And this red one right there, 2761, is a short one. So for zone 7, I have a long one and a short one. Green is long, red is short.
I see.
For zone 6, same thing. Zone 5, zone 4, zone 3.
So we have
Actually, green is short and red is long.
red is long.
The bigger the numbers are, since they've already crossed, the shorter the radius curvature.
So I would say, looking at this chart, that axis 3 sticks out as long, and
On zone 7?
on all, I'm looking at all 4 axes.
Oh, I see what you're
across
saying.
All the zones.
Yes.
And what would indicate clear astigmatism if it was always axis 3 being long and
Exactly.
always axis 1 being short.
Exactly.
And you don't have that, which indicates that you have an irregularity problem,
A bumpiness.
a bumpiness.
But the question is, what's the amplitude of that bumpiness? And it's about that big.
It's really small.
Yeah.
Yeah. So it's not even right to call it astigmatism at this scale.
Right. Wouldn't
It's-
that be more like a 2nd degree astigmatism?
Talk about higher order terms and all that.
Yeah.
But roughness, bumpiness, irregularity
Mhm.
in more broad strokes.
But would you agree it's better than a star test where you say, oh, it's blanket term, astigmatism.
Yeah.
Now all of a sudden I have localized
You have
error
localized
analysis.
error, and they change across which axis you're looking at.
Now, if I go and I work range 3, zone 5, that astigmatism for range 3 will now be a different number.
Yeah, yeah.
So I'm kind of hoping that as the mirror gets cured from these anomalies, that those numbers get closer together.
Well, except that, as you just described earlier, that's not the mirror, that's the system.
Like, exactly.
And you're not using this, you introduced it as saying, you'd be crazy to use this test to figure a mirror.
Exactly.
So,
So that's why
What
I would
do-
also take my secondary mirror out, put it on my interferometer, and it doesn't go back in until those bars are straight,
Okay.
evenly spaced, and parallel.
so given now a mirror that passes the easy Hartmann and a secondary that passes an interferometer test, and you put together the system and you get numbers like this,
Mhm.
what do you do?
I don't know, but the idea is that we make these beautiful mirrors, we stick them in telescopes, and what if it sucks? So now we have jumping off place. Well, let's fix the cell. Let's fix the acclimatization. Let's fix the draft.
Now
Let's
you're
get
talking.
rid of the heat tube along the top.
Now you talk.
Let's get all this stuff. And if I take care of 19 things and I still see a consistent anomaly, if you look at there, range 2, zone 6, would you agree that that's out of line? If I take care of everything and I Hartmann test this guy 4 times, that guy is still there. That's on my mirror.
Well, yeah, but okay, I got you. And you've got another test in your pocket that you're doing in the shop.
Yeah.
That isn't giving you that error.
Well, maybe it is, maybe it isn't.
Yeah.
This telescope here, forget this telescope here.
Yeah, yeah,
If
yeah.
I get done with Lonnie's 8 radial tests and those Mueller-Croyd graphs are all right down the middle of the line,
Yeah.
and then I put it in my telescope and it looks like this, it's like, how did that happen?
Well, you've got a cell problem or
Yeah.
or all these other things that you listed.
Exactly.
Okay,
Yeah,
I'm
Dan.
clear. Thank you.
Would it be advantageous to put the camera at the prime focus in the center of the light path?
It would be if I were mechanically as sharp as you, I could probably do that. I would have to, okay, so one of my reasons of doing this is what if Bob says, hey, I want you to check my scope. I don't want to tear his telescope apart and install a camera up front and all that stuff. I want to be able to put it in right into the focuser and see what you get. That would also eliminate the secondary mirror as part of the problem. So that might be good for a mirror maker. I know that the guys at the Ferguson Observatory put a camera at their prime focus, but they weren't doing Hartmann with it. But for me, I want to put it in the focus, do my shooting with the minimal amount of impact on the scope, and then try to analyze what's wrong. But yeah, that would actually be a mirror-only analysis. You'd still have your climatization in your atmospheric. Your environment is probably 90% of the problems, but that would work very good. Oh, this reminds me, if you shoot this way or shoot this way, you've got a image flip issue that you have to keep track of. So one thing that I do on my masks is I put another hole right here on my mask. That way I can hang it without using one of my other holes. And then when I take a picture, it's a reference to tell me which way is up and which way is right.
Brilliant.
So that helps me. So if I get an image flip, I can remember to flip that before running the process.
Brilliant. Have you thought about doing this in a double pass autopollinator?
No, I haven't. And let me breathe on this one for a couple of years first.
Sure.
Yeah, but I love auto-collimation testing. That crap is awesome. But yeah, give me a while and keep asking me.
I'm going to ask you in 5 minutes.
Ask me in 2 years. Yes, sir.
So you transfer those poles with the marker to the back.
I'm sorry, I can't hear you.
So you transfer those poles to the back of the mirror, the console of the mirror.
Okay, so if you think that about it, this mask, sorry, Zoom people, I'm showing something, you can't see it. I got this mask at the front of the scope. From the star, the waves are planar. So they go parallel rays. They hit the same XY position on the mirror as this mask. They also have a Z coordinate because of the sagittant. And then they come back in their conic trajectory back to the focus. But the XYs here are the same as XYs here. Now, Bill and Lonnie have it on the mask, and then that gives you that parallax problem where the center of the hole is a different place than where it's hitting on the mirror, which is calculatable and fixable. But I don't have to worry about that.
But on the second from the last slide, you're marking these locations of these holes on the perimeter.
Gotcha. I see what you're saying.
And how do you make sure these actually align with the mask that's at the front of the post?
Okay, so I take my mask. This is the same mask I use on the Easy Hartmann test. It just sits on there and just dead center. I flip the mirror over, set it on there, and it's now dead center again. And I make all my marks. Now, sure, there's a curve on the other side, but they're so close that when I'm working the mirror, you know, it's close enough for working the mirror.
So you take it out of the mirror and put it in front of the telescope.
Yes, what I am testing with the at the Focus Hartmann, I don't use these hangers. I have two things on the scope with bolts on them. Then this guy has two things coming down. It sits on there, and I push the two until I can center the mask up.
How do you know if the mirror is not rotated?
Okay, so first of all, it goes on like this, not like that. And then I set my camera to 6400 in 2 seconds. I take a test image and I look to see the holes. I look to see how they're getting around the secondary mirror, stuff like that. And so centering is a real problem. I don't need to center it with version 2 and version 3, but version 1, it has to be centered. And I think that's one of the reasons why I have bad outcomes with version 1. I am going to abandon that, to be honest with you. Any other questions? Any questions from Zoom land? All right, well, thank you for letting me be here.
I'll take.
Yeah, I'm gonna let you do an eject on that. I hope that was worthwhile for everybody.
Oh, I'd say so. Yes, thank you. Okay. All right. So somehow we're still exactly on time, and we have Ed Allen up next. His presentation is called Beyond Stiction and Friction: Applications of Fluid Motion Mechanics on Dobs and Other Scopes. Now, as it happens, Ed gave a version of this presentation at the Oregon Star Party in July. And it blew me away. And I would imagine that it will blow many of you away as well. So I am going to enable his screen sharing. And Ed, are you there? Hello, I see your name on the screen.
I'm here, Howard.
Okay, there you are. Okay, so you're up. Let me know if you can share your screen or not.
Okay. Let's see here.
There we go.
All right.
Okay, take it away.
Okay. I suppose everybody can hear me okay?
Yeah, very well.
Good. Okay. Thanks, Howard, for the introduction. And after the past 3 or 4 talks, I feel like this is going to be really easy stuff here. I feel like a Captain Obvious, I suppose.
Not really. Don't worry about that.
But this is really intended for a wide audience, and I've tried to put together something that'd be easy for many amateur astronomers at all levels to be able to implement if they wish. So today's talk is called Beyond Stiction and Friction, and what I'm going to do is introduce another method of controlling manual telescopes. I'm mindful that I'm providing a alternative to the inertia of all the traditional methods that were introduced 50 years ago or so. And one of the things that occurred to me is it has to meet 3 criteria. It cannot be any more expensive, preferably less expensive than the current methods. It has to be at least as easy to implement on average. And most of all, it has to work at least as good and preferably much better than the current methods. So with that in mind, let's go to the next slide. Will it switch here? There we go. What we're going to do is move on from the sliding surface model or the tribology model, which everyone knows is materials we've used in the past, like ebony star and Teflon, etc. And what we're going to do is go in a little different direction. This is our tradition we've used for many, many years with the Teflon pads and the bumpy little sliding surfaces and whatnot. And those materials produce, I'm gonna need to move my window here. This is kind of blocking me. There we go. The friction model that we've used here, which is the Stiction friction model. It's also the slip model, and we're going to be moving away from this. So just forget about this particular slide, except later on I'll kind of reference it against the hydraulic or fluid model that we're going to be moving to. It worked. Okay, so today's talk, I want to kind of put some brackets around it. The candidates are manual telescopes only, and I'm not going to cover tracking or go-tos. But at the end of the talk, if there's time in the question and answer session, I'll be glad to discuss this a little bit if somebody brings it up. There's a couple of technical reasons, and I think one of them you'll pick up immediately, you already know, and the other one may be a bit of a surprise. There's a couple exceptions to the manual scopes limitation. One is Dobs on equatorial platforms. This will apply to those. And if anybody out there has a clutched or a two-state scope, it'll also work with that. It's suitable for all kinds of scopes, Dobs, balls, equatorials, optics or null, with the exception that it does expand wide field viewings capabilities a little bit. For instance, if you were to apply this to binocular-based mounts, it could be very useful. I use it on my 24 when I want to, let's say, trace the edge of the wall in Cygnus, and I want to be able to finally move the scope around and trace large area details. So it does help with certain very fast optics with wider fields of view, but it works for all scopes just as well. Okay, so I'm going to introduce you to a new category of devices here. These have been around for quite a while. And on the right, you'll see that there's a number of terms that are used to describe them. And in most cases, you'll see that it looks like there's reducers and dampers and things like that, absorbers. But that's not the only way they can be used. And on the left here in this image is some of the units that I've been testing. I think I tested about a total of 22 of them in a couple of scopes, and I'll show that to you a little later. But they come in all sizes and all varieties. And to give you some idea of their sizes, where's my camera? There we go. So here's a little one here. This one that can actually handle a pretty large.
We can't see you, Ed, because of your presentation being shared.
Oh, okay. Stop the share
Maybe
for
at the end. Yeah, there you
okay.
go.
So this is a mid-sized version of one. This would actually handle a pretty good size scope. If you have something really small, here's a little tiny one here. Still too big. Here's one I had to put it on a wire tie so I won't lose it. Okay. And of course, they get larger and larger yet. So all kinds. There's a whole field of these things out there. And I'm going to go back to screen sharing. All right. So they're available in a number of varieties. Today, I'm going to focus on rotary and bidirectionals, but that's not the limit. There's many, many more out there. When I say thousands of physical shapes, that's a way understatement. It could be literally 100,000 shapes. They're all over the place. In most cases, they're used for speed reduction, but that's not what we're going to use them for here today. And they're all around us and often unseen. In other words, you probably have a bunch of these in your home, like on your toilet seats when they soft close, or your kitchen cabinet drawers when they soft close, or your glove box in your car when it drops down slowly, or your eyeglass holder does the same. So those are examples of motion speed control or speed reduction, but they're not the only way they can be used. Okay, there are a lot of advantages to these devices, and I'll go over both the advantages and the disadvantages. They dampen speed, and they improve fine target approach. When we look at fluid video heads in the camera business, they're often used with high power, high magnification video cameras for wildlife or whatever, for moving objects, because it gives you them the ability to smoothly move in on a target, which is not unlike what we kind of want to do. And that's where I kind of got the idea, was crossing the thought streams of working on fluid clutches for another project, and looking at the window through a spotting scope on a fluid head at some elk in the distance, and thinking, why are these two not combined, and why are we not using them on our Dobs and whatnot? So anyway, one of the underlying principles of it is that there's a variable resistance and speed and applied force formula. And basically it means that the more force you apply to one of these devices, the faster it moves. But the faster it moves, the more resistance it presents. And that's also true in reverse, in that if I apply less force, the speed slows down and the resistance drops. So it's sort of like a negative feedback circuit in electronics. The second one down here is really important for our use. And if you recall back, I showed you that sawtooth pattern of stiction to friction and transition states going back and forth. This is what this the second paragraph is talking about. We're going to hydraulics or fluid based, and we get away from that stiction friction and we move into something called basically it's just a damped shearing of a fluid. I call it breakout. And then of course the fluid can lock up at the end if we do it right. So we can get a hold for like carrying a load in a focuser. And we get by completely getting rid of those those jumps, those jerks, those oscillations, and we replace it with a smooth curve that's built into the device itself. So you no longer have to worry about tweaking a scope design to get the stiction friction as close to equal, if that's your goal, as we used to. In other words, it's all been preordained by the internal curve of the devices we're going to be using. So that whole component of trying to get the scope motion correct is basically bypassed. And the fluid motion control offers really smooth diagonal and circular movements because we don't have those little lockups. And we can do smooth diagonals, circular motion sweeps, and it also helps quite a bit in Dobson's hole. There we go. Okay. So my mouse pad tried to run away from me. Okay, so these devices are environmentally sealed, so we don't have to worry about OSP dust or moisture on our trunnions or dust or any of that kind of stuff. We don't need to do any external lubrication. That's all been eliminated too. And the first two here contribute to the third item, which is consistent motion control. It's very it's very predictable and it's always the same. These components I'm going to show you are very inexpensive. They're easily sourced. They're easy to ship. They're lightweight. They also come with published tolerances, which gives us the ability to calculate the results, and we can know exactly what we're going to get before we even build the scope. So you don't have to guess at the size of your Teflon pads or the width of your Ebony Star track or the location of the pads or any of that kind of stuff. Everything is predeterminable, and you know what you're going to get. So today's layouts here are going to also give you the ability to do encoders and pass through access cabling, etc. And I'll show you all that. Let's see if we can get here. Let me jump. There it goes. So under the hood, these are some samples of what these devices look like, so you can kind of get an idea what's going on. The one on the left is a disc style, and you can see it has multiple O-ring seals. And if you look closely, you'll see it has vertical fingers sort of inside of it. In other words, the surface area between the rotor and the body is actually much larger or greater than what would appear just by looking at it casually. If I was to spread out the disc on this device horizontally to make it flat, like two flat discs together, then you would be looking at something probably 2 to 3 times its physical size. So these are just folded into themselves in many cases. And in this case, it's a disc version, but there's also drum versions. And then, of course, there's single plane or single surface rotors and bodies. But the big thing is they can often be deceiving as to what they can actually do because of the way they're made. And another thing to keep in mind when you're designing these into a scope is the rotor and the body are interchangeable for force input. So you can go either way depending on your design. So someone who's much wiser than I at OSB told me that I need to explain how these would be applied into a couple of scopes so that during the rest of the presentation, you're not thinking about how do I get this to work with my scope. So I've moved this in or added this early on to kind of allay your fears that it's not difficult to install, and you'll find all kinds of ways to do it. This is very basic kind of stuff here, folks. This is a hub style. We have a bearing. We have a motion control device, and we have an optional coder shown there on the end. And this would be the same on both sides. Excuse me, or forgive me for my rather crude drawings here. For those who like trunnions, we get rid of the Teflon pads and the Ebony Star, and we put in some sealed bearings and one motion control device per side. And that device can be located on the edge of the trunnion, like you see here, or it can be located on the at the COR, or the center of rotation, on an arm, not too dissimilar to what you see with a encoder suspended alongside a trunnion. Very basic stuff here. In this case, I'm showing a trunnion that I've added, an existing trunnion that I've added a timing belt to on the side. Can you see this picture at all, Howard, or not at all?
No,
No?
we can see it
No.
fine. I do have a question though.
Okay.
In this case, instead of having 2 sealed bearings, couldn't you replace one of those bearings with a motion control device?
That's an excellent question, and later I'll get into more of the whys, but the motion control device does not have load bearing capacity at all.
There you go. Okay.
So basically it's a device that can only accept rotational load. It cannot accept axial or radial loads. And that's pretty much true for the entire class of devices. So yeah, you have to have a load bearing system, or you have to add load bearing capacity to the shaft of the motion control device. And by the way, and I'll get into a little bit later, but there's a couple of tenets when it comes to motion control devices being used in scopes. One is we have to get the underlying resistance of the support system as low as practical. And that's very important because of the ratio of the traditional friction versus the motion control or the fluid friction. I actually built a device, and I'll show you a little later, that I used to get a relative idea of how much of those two types of friction interplay with each other and where one kind of overrides the other. But needless to say, the amount of friction that can be underlying friction has to be relatively low, or it just starts eroding the capacity of the fluid control device to provide that nice fluid motion that we're looking for. Okay, here's another one here for an example. This is kind of like yours, Howard, where we have a couple of roller bars, and in this case, one single motion control device can do the whole scope. A little extra flexibility notes. You can use one or more devices on an axis, and I'll show you that here in a second. The torque is paralleled when there's more than one device added per axis. And also you can mix and match to some degree the values of devices. Let's say you use the formula I'll show you in a bit, and your result is 5 Newton meters. And you are looking at the manufacturer's catalog, and you pick a device, and it says this one's only available in 1 through 4 Newton meters. So you wouldn't want one side being 4 and one side being 1 necessarily, because that would mean that one side would be providing most of the resistance to motion, and you might be torquing the structure of your device a little bit, of your scope a little bit, but you might want to pick a 2 and a 3 to get your 5. So you can go on and off axis, and I'll be showing that too. Off axis includes trunnions and roller bars, and in all cases, of course, encoders and cabling are supported. I used some low-cost G2 timing belts and gears for rack and pinion. I'll show you how to do that. And that might be useful for anyone who has an existing trunnion-based scope and wants to improve the motion, but they don't want to rebuild their trunnions. And by the way, the devices can be added. You can use more than one device, like I mentioned on the first sentence here, but there's also something I call swing ends or drop ends for adjusting the torque values. Imagine being able just to push a little something and change the entire underlying mechanics of your scope so it feels completely different. I'll show you how that works. So we'll start with a little bit of easy math. Compared to everybody else's, this is pathetically easy, but I'll just go through it real quick because there may be some folks that are not familiar with it. T is the value that we want to achieve on our scope for our ability to hold the load in the focuser. And so that's the result. L is the distance in meters from the alt axis center of rotation to the center of the focuser. 9.8 for gravity, and M is the weight load in kilograms at the focuser that we want to support without the scope moving. So that formula is a good start, but it also requires a few adjustments. The first one is reduced ratio, which is usually what you get with an off-axis installation. In my case, I want to show you here in a little bit on the model of the mock model I built up, is there's a 50 to 1 pinion to rack ratio. So we take the result and basically divide it by 50. I know the formula can be written out more compact, but I kind of spread everything out to make it easier for folks to see the different components. When you're using more than 2 devices on a axis, then you divide the result by 2 so that each one's carrying half the load. In many cases, you're going to take both the top sentence here and the second sentence and put them together so that you have, say, you have an off-axis trunnion and you get a motion control device on each side. That means you would use both of those adjustments. You might want to add a little bit for wind resistance and bumping. And the next sentence is, I'll explain it to you this way. Extra counterweighting can allow for a lower T. And what that means is these are bidirectional devices. So if I size it so that my focuser can have a kilogram of load, if I have the scope perfectly balanced, and I add a kilogram of load in it, that it won't drop. It holds its position. But because these are bidirectional devices, that means you can have a kilogram of upward resistance too. So if you shift your counterbalance a little bit, you can increase your downward capacity of your load in the focuser. So you might have a ½ pound in the upward direction and a pound and a half, or sorry, half kilogram in the upward direction and a kilogram and a half in downward direction. I'm still in that American nightmare zone here. Okay, so theoretically, resistance should be as low as possible, preferably 0, but we can't get there, but that's okay. If you have a lot of resistance for some reason you just can't get rid of, then that has to be deducted from T, but you will lose some of your fine fluid motion control. The result that you get on your alt axis can be used on your azimuth. So in most scopes, the alt and azimuth L's, or the distance from the focuser to the center of rotation in both axes, it's about the same. So if you use your alt axis for your azimuth, that means you get the same push force in all directions. Okay. So here's some typical curves. Yes.
Excuse me, Dan has a question.
Yes, Dan.
On your altitude axis, wouldn't that change depending on your altitude by like the sign of the altitude?
Well, you
That's what the focuser weight, for the breakout of the focuser.
yes, that's correct, and it's the weight does increase, but the formula is set for 90 degrees horizontal.
Horizontal, okay.
Yeah.
So
Yes. Okay, so these are some of the torque curves that are typical published on these devices. And you notice they don't look anything like the sawtooth we saw at the beginning. And they have some information here that we can use to help us select. But notice I've written on here some yes and no's. So the no's represent the rated torque of that device. So if I look at the device on the left, I got a red X above 20 on the rotation speed, and then come off across here to the torque. It's approximately 0.2 Newton meters. That's the rated torque of that device, but that's if we were using it as a speed control, if we wanted to make our toilet seat go down slow, but that's not what we're looking for. We want to use it to hold the load and use its breakout. So where I've circled the yes is the point that we would want to use. So in this case, if we calculated T and it came out to 0.08 Newton meters, then the one on the left would be suitable. And the same thing on the right. The rated torque of this device, the one in the blue box, is approximately 1.2, I think, Newton meters. But we would use this if our T came out to say about 0.4 or 0.5 Newton meters. So this is very important that we don't use the rated RPM, we use the breakout point of the curve. When I'm here, we'll look at the bottom left hand. This is the temperature characteristics. Fluids get stiffer when they get cold and a little more fluid when they get warm. As you can see, the curves are pretty flat. And in my experience in testing, which I'll show you a little bit, this slight difference is basically non-detectable by human hands and human input. It has to get to be pretty darn cold for it to start stiffening up. But you can see it's a pretty flat curve. There's some limitations here that you need to know about. The first one Howard asked about was them supported input shafts. It's very important that we only do rotary loading. You can couple these with inline couplers to a shaft or a friction wheel if you want to do a friction coupling, a belt, for instance, as long as you have some external bearings to carry the load, the axial and radial loads. And the better job you do at that, the longevity goes up. Not really a limitation when I say possibly decades, but hey, it's a limitation. Disc devices. Let's see here. Yes. I don't know. I guess you can't see it. I'll show it to you later. The disc devices with square input had to be really tight and snug, or you'll get some slop. And as a slight note, if you wish, you can select your torque at maximal anticipated operating temperature. That ensures that you'll have plenty of holding capacity at the focuser for the device as the temperature up into that upper operating temperature range. And my recommended low temperature limit at this point is 0 because that's where I tested it last winter outside in the snow. Okay, so these devices have been tested. A couple other concerns. Some people think about, well, they do contain a fluid. What happens? Well, they have O-ring seals, and they can be used in any orientation. Again, longevity is highly dependent on proper force application. They use stabilized silicon-based fluids. They actually look more like a grease. So they're very stable over time. And there's some specs about cycle rates that might get people excited. You know, and things like max conditions. And one of the tests that I ran on the 24-inch was taking devices, and let's see if I can find one here. Yeah, I have some here to show you. And I installed it on the 24 with a 34:1 reduction ratio. So that means it spins 34 times for every spin of the scope on its axis. And I ran it up and down 20 times, full extension, horizontal to vertical, back and forth, no stop, as fast as I could. And at the end of that, the temperature increased approximately 9 degrees at the surface of the motion control device. And I don't think that's a way anybody would use the scope, moving it as fast as they can up and down. But at that kind of rate for that number of oscillations, that was 20 oscillations up and down, full cycles.
Excuse me, Ed, Dan has another question.
Would that
Yes.
be F or C?
I can't hear you, Dan.
Celsius or Fahrenheit?
Oh, I'm sorry. That was Fahrenheit. I'm in that American Twilight Zone. Okay, so here's the other important math to consider, and that's cost. These bearings are dirt cheap, you know, $1.50 a pop for the sealed machined, don't get stamped, but machined bearings. The sealed flange bearings are slightly more. The rotary motion control devices are about 7 to 12 per device, depending on size and capacity. There's some that are a little more expensive, but I wouldn't expect those to be used until you get to a scope the size of, say, I don't know, 36-inch, F5 or something like that, something really big. So rough total for most scopes would be to $20, $40 range. So not very expensive. I've tested, like I said, a number of these devices, and here I've provided this tile so that you can go back and refer to it later if you want to look into this. These are a number of devices under a couple different manufacturers or distributors' brand names. Each of these ones that are bolded are available in 2 to 6 torque values. Using my relatively limited number of data points, I've sort of categorized them as to which size scopes they might be useful in. And I have a warning in yellow about one particular series that's not suitable for our needs. And if you don't think that they're strong enough, you can get them all the way up into devices that are sized to settle out Ferris wheels on gondolas. So yeah, the range is quite large. So here's a little bit of the testing on the 24. I have 4 different devices here, and in this case, these are all at 34:1. They're also tested at 1:1, and the performance is remarkably similar, even though the curves are slightly different, and that's because one of the equalizers is in a 1:1. The speed is lower than the speed on the reduced versions, on the reduced connections to the scope, the reduced ratio connections to the scope. So, but when you average it all out, it's remarkably similar for all these devices. Okay, so I got a mock-up demo here I'm going to show you. These are the numbers so you can see what we're doing before I switch off the sharing. And basically I kept it really small. This is a very basic demo. There's two NM on the alt and as when there's 1 device per axis, 2.5 when I have both devices on the alt working together. I got 2 different versions. Very simple construction, 3 bearings for the azimuth, and just 1 flange on it, and then a couple of sealed bearings for the hub and the trunnion side. So, okay, so I'm going to switch off screen sharing and go to the live. Can everybody see me?
Oh, hold on a minute there, Ed. I'm going to try to make you full screen.
Okay.
So we can see what you're doing. Maybe I can do it here. Under view. Under view. There we go. There we go. Okay, go take it away. You're full. We can.
So Ed, I have a question.
Yes, Mel.
So on my 20-inch, I calculate a half kilogram, maybe a kilogram at the focuser, a meter length. So I guess I need something around 10 Newton meters, maybe 20. So having not built the scope, I'm in the ideal position to either put one of these devices right on the altitude axis itself, and then just build a fork arm up to it, since the center of gravity is going to be very short, or I can do a trunnion. The second part of my question, besides the first part being what would you recommend, is that the scope is big enough where I will grab the upper end next to the focuser, and that will exert a torque. So am I better off with one of these devices on the eyepiece side, or can I split it across both sides of the altitude axis?
Okay, I'll answer the last part first. So I always recommend, if you can, to put 2, one on each side so you don't torque your structure. If you have all your resistance on one side of the scope, you might be able to get away with it if it's a tube, but if it's a truss or some other kind of construction that's open, then you would probably want to have one on each side, and that's where we divide the T by 2 so that each one's carrying 50% of the load. As far as trunnion versus hub, that's a good question. I'll tell you what, I'll get that in just a minute because I'm going to show you a little bit about how that works, and then you can kind of get an idea maybe which way you'd like to make it go. So right now, this is a mock-up I made up for OSP. Don't laugh, folks. I made this as cheap as possible. It's not balanced well. All right. I want to move this camera a little bit. There we go. So it's not balanced well. It is really cheap, and I did that intentionally.
I just did the comment on that briefly. Having seen this, the quality on this is higher than most people's real telescopes. So even though Ed doesn't think it's much, it's really very well done. Oh, I don't know how we.
You're too kind. So this is riding on masonite. Here, a piece of masonite on the bearings. It's just particle wood, so there's not much going on there. It's just a piece of wood here. And what I've done is I've built two different styles of alt support. So not because this is what you want to do, but because I wanted to show you two different versions. The first is a hub here. All right. And right now I've got the hub disconnected because I wanted to show you the underlying mechanics, just how basically floppy it is, totally unusable. On this side, we have a trunnion, okay, pair of bearings, and a little motion control device here in the center. And this trunnion is connected to this motion control device by a little G2 belt I've added. I did this because a lot of folks will have existing scopes with existing trunnions, and this is 1/2-inch material. And I wanted to show that it's possible to put a, I think this is a 6mm G2 belt alongside a bearing on a 1/2-inch thick piece of material, and just show that it's possible. Okay, but that's not the only way you can connect it. You might want to connect it by friction coupling, a friction disc or something like that. So there's different ways you can do it. Or you might want to put a hub up here and connect it, here and still have trunnions. So there's all kinds of ways you can do it. So anyway, you've got a pretty good idea now of the underlying mechanics. I'm going to put a screw in here and just attach this. All right. Then we'll do one more here. Okay, so now we've engaged that motion control device. And now I'm going to go over here and engage this one. I just flipped it into the track. And so now you can see things have changed dramatically. Okay. Okay.
Beautiful. Wow.
Okay, so it's a huge difference. Now, one of the things here I want to show you is loading. I'm going to take this out. This is about 0.6, maybe 0.65 kilograms of steel.
Now, I will add, having pushed this around at OSP, the motions are beyond smooth as butter. It is just like super, super smooth.
Yes. What I'm basically doing here is replicating, and I'll try to move this around here a little bit here. This is a standard, there's not standard. This is a decent quality pan head, okay, on this spotting scope. All right, this is a fluid head. It's fluid in both axes. It's not a friction drive, and it's quite expensive, obviously, and it's adjustable. As it turns out, we don't need adjustment on our telescopes. We do here because this pan head might be carrying a little camera with a built-in lens, where it might have a big old video camera on it with a 800, 1,000 millimeter lens on the front. So you need adjustability because of the tremendous load range that you can see, you know, from like almost 0 to 20 pounds on this thing. Our scopes, our load range typically is whatever we put into the focuser, because the rest of the scope is pretty much static in its weight. So we don't have to have adjustable fluid dynamics. We just have to have ones that are appropriately selected for our need. Let's see what else here. Put this back in.
Can I ask a question?
Yeah, jump right in.
Okay, so I know you showed us the plots where you have the braking torque, and you said that that's where you want to operate. But even at that braking torque, you know, it had a certain RPM rate, right? So how do you know? How do you know where it looks like the data sheets you showed us didn't have the exact braking torque? How did you find that out? Like, how did you use the data sheet to figure out what spec range to be in?
The best part to use on the breakout curve, especially if it's one that comes up like this and out, is just where it starts bending the way, not down here. Okay, so try to do this here. Okay, so you got an arc. Okay, so you got an arc. So down here's the bottom where it comes up, when it starts bending the way.
Okay.
Right down here is where you want to try to get.
Oh, I see. Okay.
On that arc, and in this case here, I've calculated. This is a 2 Newton meters, and I have, I believe it was. Let's see, it was 0.75. No, 0.25. I'm sorry, Newton meter on the small one here. So together they're let's see, together they give, when you calculate it out, it gives me a load range of about 0.7 to 0.8 kilograms at the focuser. Okay.
I see.
Okay, so you know, the formula works, and as long as you adhere to that, you should be in good shape as far as load range. You might want to add a little bit more to it, and I've tried this at different levels. In the 24, I went up to a 2.2 kilogram, about 4.5 pound load at the focuser. And it worked just fine. I left it on target, a static target for 24 hours, come back later, make sure it hasn't shifted, that kind of thing.
Okay.
So
can you suppose you design it for 2.4 kilograms or whatever? Does it mean that that's the sort of force that you need? You need to apply about 24 newtons to get it to break?
that is correct.
Okay.
Yeah, and keep in mind, if your scope perfectly balanced, that's 2.4 in each direction. Okay.
Mm-hmm. Yeah.
Okay. So you know, you might want to use your counterbalance system to set it so that maybe it's only 1 kilogram in the upward direction and 3.4 in the downward.
Okay.
Yeah.
Okay, that makes sense. So that the braking is easier.
So yeah, the braking is easier, and it allows you to move the scope easier because you can use a lower amount of torque
That makes sense.
to hold it. Okay, so you're using that upward direction also. Okay, so central hub, we saw that happen here. In this case, I used a little 1/2-inch bolt, nothing fancy, to go from the scope, the wood, through a bearing with a 1/2-inch ID on the bearing, through the disc and out to the end here, and the end's bored out a 1/4 inch for a encoder on that end of that bolt. So you can just put a encoder right there on the end of it, or you can bring cables out, you know, whatever you want to do there. On the other side, you've got this all open, so you can do anything you want there.
Excuse me, Ed. We have another question. Terry, if you can hear me, just go ahead and ask your question. There's no need to raise a hand.
Okay. This may have been already addressed earlier, but I lost the connection. But anyway, my question is regarding torsional stiffness or to non-engineering types, how springy it would be on the connection. Depending, that of course depends on the shaft size and that sort of thing. What do you have to say about that?
Well, the underlying scope mechanics will still apply. So if there's a lot of twisting and turning and flexing in your an underlying scope, that certainly will figure into it. The shaft here, like I said, I used a 1/2 inch, so it's very little torquing going on there. You would have to use basically good common sense for those things. I guess it varied too much from build to build to really quantify it here. But the fluid motion does some interesting things. It does correct a lot of problems in a scope because it smooths out motion. That's one of its primary goals. Oscillations are damped. So if it's an oscillation from mechanics or an oscillation from something going on, it helps smooth it out so that it feels like it's and Howard, I think, can kind of test this. It makes it feel like a more expensive scope. It's just like, this feels much more fluid and better than a ball head on a tripod. It's just the nature of the beast.
Well, I appreciate that, but I'm a little sensitive to springy scopes from my ancient days.
Okay, there can be some springiness in the structure, and there is a tiny bit in here in the fluid head itself. That pretty much is negated because what happens is if I swing it and I load it up and let go, there's sometimes a little bit of rebound or return. But when I put it on a target and actually use it and just center it and take it off, it doesn't move at all. It erases any predisposition for any springing. And that's pretty much, if you can go like that and take your hand off it and be right on target, then you probably would never notice it because like I said, it resets. It erases itself when you just get it right on target and hold it. If I let go, it doesn't move at all. And I had a reticle in here, and I've had it on star testing, and I've had it on 24 doing the same thing, and there's no motion issues whatsoever. The reduced ratios reduce that even further. In fact, they kind of just get rid of it completely. So a reduced ratio has a slight advantage over 1-to-1 with any rebound effect or anything like that, or return. But again, it depends on your structure. If your structure has return in it or rebound, then it's going to come through. I can't get rid of that. A note here on these reduced.
I have a quick question here, Ed.
Yes,
from Rob.
Yeah, Ed, I have a go-to scope in which I built slip clutches, and they're just Teflon on Formica on those slip clutches. You said earlier at the very beginning, this is not for go-to, but I can't see why it won't work. Good.
That's a good question.
On that.
Okay. Okay. Here's a version that I put into a device or into a turning that goes in the drivetrain. Okay, and it provides a fluid clutch or a fluid motion control in the drivetrain, and so basically uses the drivetrain of the scope, your servo, your motors, your reduction gear, as the body of the scope. Okay, to hold one side, right? And the other side turns and moves with the scope. The problem is that any servo or any stepper connected to one of these outputs a pulsed power wave. Okay, it's because your PWM controller outputs generally a square wave. It puts out pulses of motion. It's almost like a vibration. It's kind of hard to feel, but it's there. The problem is fluid motion control devices like these experience a form, and I'll use the term liquefaction, when subjected to a vibrating force like that. And it causes a slow drift over time. Okay.
So in layman's terms, then the fluid is always fluid. It never acts as a solid when it's being driven by a pulse.
But that's correct. It's being shaken, and I call it liquefaction. Somebody else has a better term. I'll take it.
Perfect. Thank you.
Yeah. And that's the only reason it can't be used in a go-to or push-to, but it can in a equatorial, because you're not a Dob on an equatorial, because you're not applying force to the motor axis or to the axis of the scope. Okay, so I want to show you this little device here. This is just one of those little motion control devices, and notice it just drops in. Now imagine what would happen if I took two of these and put them here. Okay, and they would say they were slightly different or a little different values. That means that on a fly, here now, I just dropped this one out, so just the one on the other side's on. You can change the whole underlying mechanics of the scope as far as how it feels. You can make it more resistive or less resistive. You know, you can't do that with the traditional model. You can't physically relocate your Teflon pads very easily, or change out your ebony star strip or things like that. Change your patch shape and that kind of stuff. But here, you can just by flipping it in, we can change the underlying mechanics of the scope, make it feel different. If you have a windy day or something, you might want to step it up, make it stiffer, just as a for instance.
Yeah, Dan has another question.
Yes, Dan.
I was wondering if the frequency of the PWM, getting back to the servo thing, would that make a difference? I mean, could there be a high enough frequency where it wouldn't be transmitted to the? Supposing your actuator was right on the axis, and you had a motor that had several reductions, things like that could be driven down, so to speak.
Yes, I've had it. Yes, I've actually spent about a month doing exactly that set of experiments, a couple different versions here. The frequency, I have been examining the frequency problem. I have not found a solution to it yet. One thing that does help to some degree is adding a small amount of, actually not small, but a significant amount of standard friction to the fluid motion device. In this case here, there's a set screw here. This is actually the fluid device here, and through it is through this axis is another disc inside of here, which has adjustable friction. It's a Del Reynolds polished steel plates. So
Could you hold it up a little higher, Ed?
Sorry, yeah. So that in this case here, I can parallel. It's like two sets of clutches mechanically in parallel, not series. I'm sorry, yeah, in parallel, not in series. So that the force is applied to both of them through the central shaft, and if you increase the friction to the standard friction to the point of where the motion disappears, or the drift disappears, then you defeat the fluid motion action. And I've tried a couple of, and I have some pictures. Well, I won't show you. I have some pictures here, but the other devices have been tried. I've had this in a complete drivetrain in a finished scope. 3-to-1 reduction, no pitman at the I'm sorry, no gearbox at the pitman, plus a 3-to-1, plus a 51 harmonic drive, and then the motion control device. And in between, I've tried elastomeric inline shaft vibration reducers. I have tried mass in the form of flywheels and a few others. but it doesn't seem to matter that any of the above will, it transmits enough through to cause the liquefaction. So it's pretty sensitive to it.
That's really amazing though, what you've done and testing on that. But I was wondering if, oh, I lost my train of thought. I think it was having to do with the stepper motor versus the, oh, I know what. So are you using a servo 1 or 2 to test this?
Servo 1, which, you know, it's a PWM output.
Well, it might be worth an experiment, and I could get you a force one that runs at 4 kilohertz instead of 2 and see if that makes a difference.
We could try it. Frequency was one of the things I wanted to investigate further, including the overall size of the fluid disk, and obviously where the reductions are. I tried it on both sides of the harmonic drive, and that made no difference. So that would the harmonic drive wouldn't change the frequency, but it would change the torque level applied to it, and none of these have made any difference. It's remarkably static as far as the results.
Wow, that's amazing.
Yeah.
And
So,
can you? Sorry, go ahead.
go ahead.
No, I was just asking if you could somehow couple it to your drive system, either through the sort of clutch system that you developed with the capacitive sensor and the linear actuator, so that you engage the fluid control when you disengage the motor, or even use like a mechanical limited slip clutch to switch over from the servo motor to the fluid controller and then back.
Actually, I have that installed on my 24 because it's a two-state. If you recall, one of the early slides said that equatorial mounts and two-state scopes it can work in.
So that's what you call two-state. Okay, that makes sense.
Because when the clutch is open, it performs like a manual scope. So therefore, I have on the end of one of my roller bars a motion control device. So it has that fluid motion, really nice. When you got your hand on the handle and it's clutched, and when you take your hand off the handle, of course the drive system is re-engaged. The fluid clutch doesn't matter at that point. It's just another little tiny load that the motor, the stepper pulls along. In this case, according to the SciTech current meter, it's indetectable. It's so small. So yeah, it works just fine in a two-state clutch system, because you have, in essence, a manual scope when its clutch is open. So it works great.
I have one more question. Sorry.
Yes, sir.
I'm dying to know the F ratio of that 4x4.
Very good.
Limiting magnitude.
This is for cloudy nights. Okay. So any other questions regarding the mechanics, I guess?
No, I think we're good here. Oh, no, wait a minute.
Tell us a little bit more about the fluid inside of different ones. I missed that. I came in about a minute late.
Oh, okay. Yeah. These devices, let me pull up a couple here. So they all have, put a guess weight background. There. And these are all in a smaller range of devices, or they go much larger than this. They most of them have a thick silicon, a specialized silicon grease inside of them. The viscosity of the fluid or the grease determines, and of course the plate area, the total surface area of these plates determines the amount of force that can they provide. And so in many cases, like this device here is available in like 4 different values, but it's exactly the same device. It's just 4 different viscosities of fluid inside. And that's how they get a range of values. There's tolerances, and that's all specified in most cases. Like on the big ones, it's like 10% plus or minus. On the small ones, it can be high as 20%. That's kind of accounted for in the formula a little bit. There's a little bit of leeway there because you do get small variances in the product specifications, but we do have specifications to go with, so to work from. So that's why we can predict what we're going to have at the end.
Any particles in the fluid?
Any particles in the fluid? No, not that I'm aware of. It's just it's a stabilized silicon grease.
And where do we get these?
Oh, you can get most of them off of Amazon. You can get all your bearings from Amazon or Easy Bearings or someplace like that. So they're very inexpensive. Or you can order them directly from the manufacturer. That's where I get most of mine because the product range in Amazon is not necessarily the entire spread, and you can get more by going to the manufacturer, but the price is about the same.
So the Stiction, you think it comes from the O-ring?
The Stiction?
What makes it stay put right there with torque on it?
Okay. So if you go back to that picture of the under the hood, what's inside, you've got in essence 2 plates, all kinds of shapes and sizes and fingers and stuff, but 2 plates a certain distance apart with a fluid in between, and that fluid is thick. It can be a grease, can be a very thick grease. And basically, when one side turns, it turns the other one. It's not a thin fluid like, say, in an automatic transmission of a car. It's pretty thick, so it translates straight through. One real quick, I know I'm a little over time here, so one real quick point I'd like to make. I totally forgot about this. Was on the 24, I ran a test. This was more for just I wasn't shooting for imperial data, just kind of wanted to qualify what was going on. And that is, how slow can you move it? How slow can you move a scope with a decent underlying mechanical system with a fluid motion control in it? How slow can you physically move it? So once you break the motion, get the molecules of the grease in motion, once you hit that break point, when you come back down, when you're slowing down, that point just keeps going down. It doesn't stop like that the Stiction friction model does. It just keeps diving. As long as you're keeping those molecules kind of juggling around inside there, it will continue to move. So the test I ran was putting a laser 30 feet from the scope, taped a tape measure to the wall, and I'm back to Imperial here. And I spent 3 minutes after I got the scope moving. I just left my hand on the side, just slowly, just kept a little pressure on it, and that the beam moved. You can't see it moving at 30 feet, but it moves slowly in 3 inches in 3 minutes. That shows you just how slow you can go. That's roughly what it's about a half a degree, pretty close to guide rate on a scope. I don't know if anybody can move a Stiction friction model that slow and be able to. If I just put pressure on it and keep pressure on it, once I break and come back down and just keep that pressure on it, it just keeps moving slowly. Once the pressure is off, molecules kind of lock up and everything stops and it's ready for its breakout for the next move. So that's kind of how it works, if that makes any sense, folks.
Mm-hmm. Okay, I think we understood. So any questions out there in the Zoomiverse?
2 chats, it looks like.
Yeah, you already saw those as we came up. So, okay, well, thank you very much, Ed.
Thanks, guys, for your time. Captain Obvious out.
Okay, we're going to take a short break here, about 10 minutes or so. And I'm going to pause the video, and we'll be back soon.
I gotta get me some of those.
Oh,
Those are cool.
It's great stuff.
I didn't even know they existed.
No, I didn't either.
Yeah, one of the classic bugaboos we have with these these Dobsonians are doing at the high school is that you get them all balanced and such, but they're still way too slippery.
Yeah.
In fact, the last one we built, we just took the Formica off and ran the, no, we took the Teflon off and ran the Formica right on plywood.
Yeah,
And the student was like, oh, that's so much better. I'm like, okay, as long as you're happy.
yeah.
But this, that little tiny thing,
Yogurt does that.
that would just solve our.
Oh, there, Mel is going to be putting those on his 30-inch
No.
to replace this Teflon.
Would you like to have a comment on this? Okay, so I asked him, oh, yeah, we have one of those 10-inch jobs that came from China with those awful spring things. So I asked him if he thought this would help, and he said possibly. Okay, but then his comment about, well, it doesn't, the concept doesn't work with push to or go to. Well, what's the difference between manually pushing your scope or pushing it because you're guiding it with a
Whether
push
or
to?
not you have a motor, or not. Does it have a motor?
No,
Then it's gonna work.
because isn't that what push?
No,
to-
push two means that it's a computer-driven Altaz telescope that you can just, it's tracking along, and then you go, I want to look at something else, and then it keeps tracking. That's
Oh,
what Howard
but we
uses.
use push to mean like using settings or digital settings.
Legislation.
That's
No,
what
it
we
doesn't,
use.
it doesn't have a motor, then you're right, it is a push-to scope, but that's not how we're using the term in this
Push.
context.
Okay, because I'm
Yes.
like, that
Yeah.
doesn't,
Yeah.
yeah.
It's just
Okay.
yours is just a Dobsonian. That's all it
It's a
is.
job, but we're using digital settings.
Yeah, that'll
And we're
work fine.
pushing it. 'cause
Yeah,
it
yeah, yeah.
doesn't, like,
You're
go
totally,
by
that's a
itself.
perfect scope for this application.
I think so, but
Yeah.
it's really nasty when you go to like, and it's like boing.
Yeah, well, I know,
Or-
those things are terrible. They're just terrible.
Keep it in your mind, Tim.
No, that.
No,
I probably.
I'm gonna-
No, this would be I think this would be a perfect telescope workshop project.
Yes.
Because it's kind of self-contained
Mhm.
and it could really improve, you know, the operating.
You're absolutely right.
Operation is-
And I want to see this
Yeah.
be adopted on these simple Dobs. And just get rid of the Teflon and Formica problem. Now we're into skateboard bearings, but those are done a dozen, so, yeah,
Hard to get Evan started.
No, yeah, no Teflon, no
right.
any type of laminate.
Right.
And the feeling of the motion
Yeah.
is so superior.
Yeah, I bet it is.
Just imagine how nice it would be.
So you can sit there and track a planet at 400x and just be like,
Oh, no, I'm sure.
Hey,
Someone
where you
was
get some of
breathing.
that?
Depending on how big the scope is.
wow.
But anyway, yeah, it was really, really impressive to actually grab that thing and push on it. It's like, holy crap, this is like, you know, $10,000 telescope motion. Yeah, yeah.
With all various loads, so this is just one load.
Yeah, yeah, there's a zillion of these. Yeah,
It'll work with any load.
yeah. Yeah, it's really, you know, again, thinking outside the old box.
Yep, yep. Yeah. Well, it really helps me to just understand how the fluid system works. Did he, in that demo, did he have a fluid on the azimuth axis as well?
Yeah.
He did, okay.
Yeah,
He
yeah.
just wasn't showing it to us.
Well, you could
From
see it from
bearing.
time to time, but he
Okay.
didn't point it
Yeah,
out.
okay,
Yeah.
okay.
But it's the same thing. It was just right on top of the center bolt.
That's what it is. Okay, makes sense. If it weren't Saturday, we could walk over to Granger and see what they have. Well, I can get online and see what they have, even easier. Yeah. You can have a hot beverage at the same time. I haven't been in there, so I don't think you can walk in there. Yeah. I've only always ever used, well, since I retired, I've only had a cash stay, but they don't restrict you like they used to. You used to have to have some kind of business connection. Yeah, but I don't think they are strict on that anymore. Right. So I just walk in there and basically. Only once or twice a year, even. Oh, we haven't seen you for a while. Yeah. Well, I've ordered stuff from Granger online just using my credit card. So I know that that's an option. I didn't know I could just walk in. I've gone in there with just a sample and the powder guys are pretty good. They figured out what it is.
Rob, I have a question. To me, it's the initial startup of moving the scope where you break free. That is the problem. To me, it seems like he still has that. Then he can slow down and not have a lower limit. But to me, it's that initial startup that causes the person to do this.
Yeah.
Am I missing the point?
No, I think you're spot on, but I think what happens here is that because it doesn't have, it still has the stick, right? It's not going to move until you apply X Newton meters as per your calculations. But then when it starts moving, it just moves. What you want your Teflon to make it do. Where so that C shape is gone, it just connects. When it just starts moving. Right?
It's pretty cool.
That's the message I got. I haven't tried it.
I've never heard of these things until today.
Exactly.
Me personally, I've never heard of this.
So, fluid head, like on the video tripod, but how does that apply to our fluid head over and over and over again? Yeah. Now I know what a fluid head actually is. And many applications time.
Howard, do you have one of these on your scope?
No,
Oh, you gotta put one on?
no, because of all the problems he just talked about with having servos right.
That's right.
So,
Right. I did.
and I don't have a two-state clutch. This is the clutch that's always engaged.
But you
So,
don't have a motion problem at all, do you? So,
no, I really don't. So that said, it would be nice to have that really wonderful, smooth fluid head
Like-
motion
like
when I
Mel.
was pushing.
like Mel. He,
Which Mel, yeah,
he's not gonna put a drive on that and he could actually maybe benefit from this.
well, he plans to put this on his third, get rid of the Teflon and laminate.
I was just saying that I've got these high school kids building these cheap dolls, and we end up with bearings that are either way too stiff and sticky, or they just flop over, and there's no middle ground. And
Yeah,
I've
it
got it, $10 or less. Yeah, just do it.
Yeah,
So
yeah, I had never heard of that until today.
Yeah.
I got another question for you. Not today. Somewhere along the way. I want to have a conversation with one back there. Field guy.
feel flattened as well.
Feels like that. Yeah. I want to get a handle on that. So I think that could be my concept.
I think you need to go to a workshop on asking talk to asking me to be friends. I'm not good enough to actually give you the explanation that it's gonna have.
I don't know nothing about asking.
You want to start at the beginning with somebody who really knows it.
I got two friends that go get it.
Good, start with them.
They're called Bill Fletcher.
Yeah, yeah.
So basically, you can take every single spell in that picture down to the level of where the background is black.
No, the point is so that there's no slope on the pedestals. So you have to draw. Good.
Right. So if your background looks like this, for example, right, here's your sensor and it's bright in the middle and falling off at the edge. It's typical fall off, right, at the edge of field. And you got all these pedestals sitting on top of that. You know, let's say the pedestal is right here. When I add that pedestal to this slope, the pedestal is going to come out like that, sloped over, right? And when you go into image J and you ask, well, where's the center of mass of this thing? It's going to bias it toward the high end, right? So field
It's actually
flattening,
worse than that.
yeah,
It's taking the center mass of this area.
yes, yeah, you're right. It's totally going to bias it toward the high end. Yeah. So field flattening, what it does is it says, okay, I'm going to take this image without any of the pedestals, so I'm getting the full flat field, and then I'm going to divide one by the other, and the result is a flat line. Now it's not zero, but I don't care because
It's even.
it's even and my pedestals will be flat and the area around it will be flat and I'll get the centroid by golly.
It's called flat. What's it called?
Like field flattening. And the way you do it is by taking a flat field image and putting that in your image process.
So I got a couple of gurus, photography gurus, and I'm going to hit them up with it. Field flattening. Thank you. You're welcome.
So when
I'll
I
let
did
you
it,
know how this goes, by the way.
yeah. So here's the bugaboo, right? When I did it, I get this. Here's my mirror, right? I don't have any mask on it, and I just take that picture, and then I go very carefully and I place my mask on there, and I don't want to bump anything on my stand or
On the
anything
picture
like that.
itself.
Huh?
On what now?
So I got my mirror sitting here on its test stand. Here's the test stand, right? And it's got a couple little supports and a clip and all that. And I take that picture and I get this illumination on my sensor, right? Then I go and put my mask on, and you got whatever your mask looks like. You got to go flip it on, and you got to not bump your mirror because that will move your illumination patch on your sensor. So you got to be very gentle with it. Everything should be locked down real tight. And if you're not, then when you get all done, your flat field, instead of being a gray uniform illumination like that, you might end up with something that looks like that, where this is really bright, right? And then you bumped it.
So this is almost like a bias correction.
Almost. There is something called a bias correction that is different.
I can
Yeah.
see this in the shot, but in the scope, I'm pointing at Polaris.
Yeah.
No mask. I shoot a picture.
Yeah. Yeah.
So what I'll have is the whole mirror will be illuminated from Polaris.
That's right. Yep. 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 As long as your guiding is good, you should be fine.
See, to me, that means that the light from Polaris will be overwhelming the whole thing. It's a background sky illumination that I'm actually kind of concerned about.
Well, so that isn't going to change, and that's going to come right out in the math. It'll take the background sky out.
What if I move the scope a half a degree over and shoot that background sky and subtract it from something?
Now, actually, yeah. So let's not think about the background sky. The background sky is probably really uniform. But if you're out, by your house and there's street lights and there's who knows what all around coming in from the sides,
I do.
is it open tube? Or is it?
Tell you how bad it is.
Yeah.
I got my scope pointing to Polaris. I got this hand covered right over there,
Yeah.
and this hand activating my shot. It's bullshit in my house.
So now what you can do is kind of the reverse.
Testing 1, 2, 3. Is anybody there?
Your mask, so no light comes in, but all the other light can come in from around the sides, and use that as your dark frame. Right. So and then you might still want to do a flat for various reasons, but okay. So in your case, you don't need to do a flat on a star because your point source is uniform. But I was using an LED, and I had huge fall off across the mirror diameter that I wanted to
Give us a few minutes here, Dale.
That's why I did it.
Okay, I've been waiting.
You don't do it. You need to do a flat field, but if you can't in your ambient light, you want to do image calibration, which is flat field and dark frame and all that. You want to do all that. You need to talk to your astronomical friends. So that makes sense. I'm not good enough at it. You just can't lay them out. What they'll do is they'll tell you to see
Ready to start. 10 minutes goes fast.
You know how things are going on. Yeah, that's. I will let that was pretty because we just felt that thing. Huh?
Oh, yeah, it's amazing. Well, let's talk about it after
Yeah.
the last two presentations.
Yeah.
We're ready to go.
You ready to go?
Yeah. We're ready to go, Dan. So,
Okay.
all right. So, okay, 10 minutes goes fast. It always does in these workshops. So next up is Dale Eason. See him here on our screen. And Dale's going to talk to us about his SkySolve plate solving finder, which I have had some limited but very gratifying success with. So take it away, Dale. Oh,
Okay.
got to start recording. Yep. Hold on. Okay, we're recording now.
I need my screen shared.
Okay. That would be here. Well, that's a really big, cursor all of a sudden. Hey, can you? Should be able to
Okay.
share now.
All right. I just have to pop up a little deal. Here's my scope I'm working on, and I'm going to try to do Ed Allen's thing he just presented on the bottom of it. So just thanks,
There
Ed,
you
for
go.
presenting that. So we'll
Okay.
see
Yeah,
that later on.
your presentation's coming through really, really well.
Okay, good. Now, if I can remember how to start it. My screen is covered up. My screen is covered up with there we go. Slideshow. Okay. Yes, I haven't done slideshows on Zoom before, so I'm a little bit out of my element here. Here we go.
That's okay. We all are, or most of us anyway.
On my screen, I've got half of the Zoom covering up my screen, so I can't see what I'm presenting.
Oh, well, we get the whole screen here.
Okay. Let me see. I think I found, there we go. I got rid of it on my side. All right. So, as you said, I have this thing called the plate solver, and it's a finder for push-to scopes. While you guys were on break, I heard some of you talking about definitions of push-to. My definition of push-to is a scope that has no motor control on it, and you have to push it around the sky to get where you want to go. And so without go-to or motors control on it, it's kind of hard to find things. Our old star hopping is fun to work with, but sometimes it can be quite a pain when I'm trying to find things. And so I wanted something that could hook up to be mounted on a telescope that tells me where my telescope is looking without having to put encoders on it and that kind of thing. So here's a little bit more about it. Of course, it attaches to your telescope like a finder. It sends telescope view position to Sky Safari over its Wi-Fi, and no encoders are needed.
Dale, we still only see the first slide of your.
No, we don't. We see his Fusion 360 desktop.
Oh yeah, that's what we're seeing.
What should I do?
Minimize fusion.
I can't understand. I can't hear.
Okay, so Dale, what we see is your Fusion 360 file of your 16-inch.
Isn't that interesting? How do I?
Yeah, it's a really cool looking telescope.
But
Good thing that's what was on the other side.
Can you minimize that?
all right. Now, do you see my slides?
No.
My
Dale,
screen.
Dale,
my
do you have a dual monitor setup?
No.
No. Okay. Stop sharing and then let's do a reshare because you might have shared your Fusion application. You really just want to do share desktop.
Yeah.
Right.
Yeah. So go to your.
Oh, there we go. I understand now. That's what I
Okay.
want. I think I'll say click on that and share.
Don't worry, it's all through experience. There we go.
All right. Now, if I can get my slideshow started again. There we go, the slideshow. Sorry about that. There we go. You see this? See a slide of SkySolve?
Yep, you're good.
Okay. So you heard my words. I probably don't need to repeat those, do I?
Yeah, it wouldn't hurt.
Okay, so Um, SkySolve is a plate solving finder, and of course, I haven't described what plate solving is, but it's just basically a camera that looks up at the sky and then sends information to Sky Safari about where it's looking. And if you have it aligned with your telescope, then it also tells you where your telescope is. And like I say, I wanted something that I didn't need encoders for, and basically is as simple to use as a regular finder and mounts like a finder. So here it is, attaches to your telescope, and there it is attached onto my telescope. It uses a Raspberry Pi inside of it, and that is powered by a external battery pack that I have down here in the bottom of the telescope. Here's another view of it. And for me, I like to use a tablet. And so I have Sky Safari running on my tablet. And there is a Wi-Fi link either to your tablet or to your cell phone running Sky Safari. In this case, do you see my cursor on the screen?
Yes.
Okay, so in this case, I've already told Sky Safari about what my field of view looks like. And I have connected the telescope, connected to my SkySolve actually. Sky Safari thinks it's a telescope, but I've told Sky Safari it's a push-to telescope. And here's a close-up view of talking to my tablet, which I like to use. This is a Samsung tablet. It makes a very nice display that I have attached to my telescope. Then, of course, you need to get this aligned with your telescope. And so besides the device itself, there is a mounting underneath it. And here is the whole thing. All the parts are 3D printed. And here you can see you can adjust the azimuth, and then this other control adjusts the altitude. To begin with, I made the knobs black, but I discovered when I'm outside at night, I can't find those knobs if I want to find them. And so I made them orange because that's the easiest color filament I could find. And they show up better under a red flashlight. There inside, you can see the Raspberry Pi. And then there's a switch on it here that I'll describe in a little bit. So the case that this all mounts in is actually keyed, and it will mount in onto that mount we just saw. And so you can take it off and not disturb the mounting position. As I say, it also has a switch on it that you can use to tell it to provide its own Wi-Fi or to use your house Wi-Fi. The switch also has another function we'll talk about in a second. Here is the mounting with the keyed. It's a standard tripod mount, 1/4 screw that screws up into the mount of the SkySolve case itself. So as I said before, the toggle switch has a couple of uses for it. One, you can have it when SkySolve boots up, it creates its own Wi-Fi system, which we call a Wi-Fi hotspot, or you can have it boot up so it talks onto your own house Wi-Fi system. Secondly, Raspberry Pis don't like to have their power yanked. They quite frequently will garbage up their micro SD card if you yank the power while they're doing something to it. So I have created a system that if you throw the switch into the opposite position of what it powered up, it waits 6 seconds to make sure you didn't just throw that switch accidentally. But when after 6 seconds, then it starts flashing the LED light that you can see inside on the Raspberry Pi. And when it flashes 9 times, then you can pull the power plug. The device itself, as I said, you usually don't need to use the user interface. I haven't said that yet, but it has a user interface. But as if everything's all set up, you don't normally use its user interface. It just talks to Sky Safari and tells it where it's pointing. However, there are some instances where you probably want to first focus that camera on to get it focused on the night sky. So you can bring up a browser interface on your cell phone or your tablet and link into my SkySolve system to help adjust the autofocus. And you can do other things with it as well. But once it's set up, you never need to use that browser interface. But we'll talk a little bit about the browser interface. As I said, it's not essential, but you might want to focus the lens if you've moved the lens around a little bit. It will give you, the browser interface will give you a live view of what the camera is seeing to help you align it. You can change the solve parameters that it uses inside. Maybe you put a different lens, maybe you want a different lens to give you a different field of view. I didn't say it before, but the field of view with the lens I normally recommend gives you about a 13-degree wide horizontal field of view. You can also change the camera parameters like its shutter speed or the image size or the ASA rating of the camera. I have it set up for what I like to use it on the sky, and that's set up as an ASA of 800 and a shutter speed of just under 1 second. And I use the camera resolution that gives me an 800 by 600 pixel range. That gives me faster solves than the camera using it at max resolution. But the camera solves are fast and have enough resolution to use. But also, if you don't have a digital camera, you can use that web interface to take pictures of focal, Ronchi, or even interferograms back in the lab. So here's what the interface looks like on my tablet. On a phone, of course, it kind of resizes and you don't get as many buttons across the top. They scroll down and you get more in a vertical alignment. Here in this one, this is what my camera was seeing at the moment. I had it just sitting out in my Bortle late sky here on my driveway, looking straight up. Camera, I didn't have it on tripod or on my scope or anything. I was just playing around with it. And this is the view. I don't know if any of you can recognize this view. For me, it's kind of upside down, but it's Hercules, and there's M13 right there. I thought that was kind of cool. Now, with my interface, you can have it set up so it will draw what it thinks it sees there. It takes longer to solve, but I have that. In this case, I would click on the interface, and this is then what it showed. And there now you can see the outline of Hercules. So you wouldn't actually have to have it talking to Sky Safari if you didn't want to. However, the images that it can put up on the sky are much more limited than Sky Safari. So I really do like to use it with Sky Safari. At the same time, it also tells you some of the stars that it found here and that it found in its display here. So I have the camera just pointing out my window over at my neighbor mowing the lawn, just to show you I have the camera params now set up here where you could change the shutter speed. And of course, during daylight, I have to have the shutter much faster than I would at night. And in this case, I've lowered the ASA to 100, and I still have the image resolution of 800 by 600. And I've told it I want JPEG images. On the display, sometimes it's too light or too dark, and so I have plus and minus where you can brighten and brighten the image or darken the image. And I have a little special image button right here you can click on. That downloads whatever's on the screen to whatever you have running your browser. And that's where you could use this as a camera if you wanted to. Also, if you wanted to change the plate solving parameters, there's a place there, you click a button, and I have various settings already set up saying, well, if you're using a 25 millimeter focal length, use this one, or if you're using 16 focal length lens, use this one. And I have some demo pictures as there, and these are the settings you'd use to solve those demo images. Some of the things you could set down here is how long it might take. If it wasn't solving very fast, it might take some time, and you limit it to 30 seconds. It turns out now 10-second limit is plenty fine. This next one tells it how many stars to look at. It looks at, in this case, the 20 brightest stars. And this is kind of a magic number that you have to go read about the solver program that you can, but set at 9 and typically work. Like I say, you don't normally play with this unless you just want to play. So here's the demo images that I have taken with it, and I wanted to show this just because the images don't have to be all clear. They can be looking up through the trees. And so here I have Orion's shield that I was looking out my backyard window and up through the trees at this one. And this solved because I have drawing the graph. It took about 3 seconds to solve this once it took the picture. If I don't have it solving the graph, it usually solves in 2 seconds or less, and then sends the solved position to SkySolve as soon as SkySolve asks for it. Here's a case we have a pretty obscured with several trees and a power line, and yet it was still able to solve. In this case, it's Aquila. And I threw this one in just to show it doesn't have to see much of the sky to actually solve the image. And as an aside, I have a customer who is using it who lives in Wisconsin, and at Madison, Wisconsin. Turns out he's a professor at the University of Wisconsin at their Washburn Observatory, which has a Clark refractor 15-inch scope that he's using this on. And he says the scope is mostly in the picture, and the observatory shutters are up there, but he sees enough to use this. And now he has students using this in his light polluted sky. That refractor wasn't very useful, it was hard to find things. And now he has students using it and finding it. So I was kind of proud of the fact that I'm attached to a old Clark 15-inch refractor. Then here's another image from my front yard. And finally, here's the Big Dipper. Just had to throw that one in there. So I've shown what it does, and here's how you kind of use it. You, of course, attach it to your telescope, and now you want to align it to the telescope. But first, you have to connect it to SkySolve, and then SkySolve will tell you where it's pointing. You attach it to the telescope by usually the device is creating its own Wi-Fi, and so you'll pick up your telephone or your phone and go to its Wi-Fi selection, and you'll find this device is one of the devices. Each device that I create has a different device, so you can have several of them out in the field and not overriding one another. Each one has a unique serial number. So then, of course, you check to see if what's shown centered in SkySolve is what you have in your eyepiece. And if not, of course, now you can adjust the finder with those wheels I showed to get it to about every 2 seconds, it'll show you where it's pointing. This can be a little bothersome to begin with, but you only have to do this once, and usually then it'll always be right with your scope. There is a feature of Sky Safari I haven't used where it says you can press the sync button. And so no matter where you are, Sky Safari syncs and says, oh, okay, I will sync to that object. Like I say, because in light pollution, I can mix up what stars in the eyepiece and get the wrong one. So I tend to, when I'm out aligning the thing, I try to find some messy object instead of a star, because those are much easier to recognize. So quite frequently I'll use M15, but one night I actually used M51. I have used M57 as well as my alignment object. So, of course, finding an object, you just look in the screen in Sky Safari and see where it's pointing. You can move the screen around in Sky Safari with your fingers, and then it's no longer attached to the scope. But you can use then Sky Safari to go find something that's of interest and then tell Sky Safari you would like to search for that object. And when you do, then you can push the search to button on the Sky Safari and it'll show you the arrows where you need to move your scope to. It usually takes up a couple of seconds to figure out what it's pointing at. And then you move your scope and wait another couple of seconds and then see where it's now pointing at. And eventually you become adjusted to how much you have to move the scope, and you usually get there in 1 or 2 pushes.
Dale,
So
how frequent are your solves now? I know earlier there used to be once in 10 seconds, but I know you've made drastic improvements to them.
the solves happen are based primarily on the link to the camera, how often the camera is updating, and how often it takes the solving information to solve and come back to it. And usually, as I say, it takes 1 to 2 seconds. It can take up to 4 to 7 seconds. For instance, if you are moving the scope when it took a picture and it's so blurry you can't figure out what it is, it may take up to 10 seconds before it gives up and says, I'll take another picture. In that case,
okay, that makes sense. Yeah.
Then Sky Safari itself won't update. However, if you have the browser interface on, the new information now, and you've clicked on the screen, it makes 2 different beeps. It beeps once if with a very low beep if it failed to solve, but it also beeps with a high beep if it did solve. And so you can have that annoying beep in the background I call it annoying, but I think Mel has used it that way for a while. When we were debugging the system, it would quite often hang and we weren't getting any beeps. And now it does beep quite often and it doesn't hang anymore. Howard and Pierre and Mel Bartel all have the unit, and maybe they can comment on how well it's working for them now.
Well, I'll say that the first experience when it was hanging was really frustrating because
Yes.
I saw Mel's unit in practice in use at OSP, and it was brilliant. I'm like, oh my cow, I need to get one of these. So I did, and then as you know, it didn't work right away. But after you fix the bugs, I mean, it's just beautiful. It's the simplest thing in the world. And especially in a light polluted sky, where star hopping is pretty much impossible, it makes all the difference in the world. So, like for instance, Uranus is not too far from Jupiter, but it's in the brightest part of my sky, right over Portland in the early evening. And the only way I can see that is using the SkySolve, and it's a snap. It's really fun. So yeah, this makes using my scope at home so much more enjoyable because now I can find stuff in the entire part of the sky instead of just in the darkest part.
Yeah, and Pierre Lemay here. I will testify also that I was, I think, the second person to, other than Dale, to try out this camera a year ago. I've been looking for something like this for a while because I use a 20-inch ball scope, on which you cannot attach any coordinate location system, and this is a great feature because you can use this attached to the ball scope to know where you are pointing, and then you move the scope around and you eventually get your object. I've had the hanging software problem for most of that time, but sometimes it would work great and sometimes it would hang. I haven't had a chance to try the new software which Dale sent me, but that's something that I will do in the coming days now that I've finished one project. But I've had the chance to try it at Stellafane last summer, and I think I found Neptune or Uranus using only the software, and I wouldn't have been easily able to find it because all I had was a reflex finder, and with the software I was able to get it right in the center of the field immediately, so it was great.
Yeah, that's a kind of a funny story. When Pierre would report that it would hang, I thought I wasn't seeing it hang. Mel didn't report that it was hanging. Both he and I are kind of computer gurus, and when it did hang, we didn't really think it was a hang, and we just would relink to the browser, and that fixed the bug, and it would start talking again. And it took Howard and Pierre to convince me that there was something going on. And once I finally figured out that it was hanging, discovered how I could make it hang. Then I found the bug, and I think we've got it all working now. Good.
Yeah, looking forward to it.
Like I said before, one of the features that I really like now is that probably none of you have used yet, is if you do have the browser interface up and you have the camera parameters turned on, you can click on that button and we'll download what it's saying to your cell phone, or in my case, my tablet. I take that back inside and look at the pictures of the sky that I was seeing, and kind of can review then what I had seen. And I kind of enjoy looking back up at those pictures it took. I was surprised one night to discover that where I couldn't see Andromeda, it saw the little blobby Andromeda feature there here in my Mag 8 skies. Let's see, I'm trying to go to the next slide. Let's see if I can. There we go. Oh, here's how you can make one. Well, there's instructions for making one. I have them up in GitHub, and if you have a 3D printer, you're set to go. I actually forgot to even tell you what's inside of it. There's a Raspberry Pi Model 4. It uses a Raspberry Pi high definition camera. They call it the HQ camera, which takes C-mount lenses. And so you can put almost just about any C-mount lens on. So C-mount lens, you can find a lot of 25 millimeter security camera lenses. You can put one of those on there, and that's what I did. And or you can actually buy a unit from me if you want. I can print them up, and that's what Howard and Mel did and Pierre did. And or you can want a case and I can print cases, or you can just want the software and I can send the software. As a ballpark price for a completed one really depends on the price of the Raspberry Pi. And when I got finished with this before the pandemic started, I figured you could put a whole unit together, including the battery pack and cable, for about $180. The Raspberry Pi's gone up a bit, and so other parts have gone up a bit, but I think you probably can put one together for around $200, or maybe perhaps less than $300. And here's a Fusion 360 view of the just the camera components and its mount that are all 3D printed. And then there is my telescope that is going to go on, and there's the telescope in the back that it does go on. And any questions if anybody wants to ask?
Yeah, I have a couple or three. So how accurate do you believe those plate solves are? Like say in arc seconds per minute?
I'm sorry, I couldn't quite hear you.
How accurate do you think the plate solves are in arc minutes and arc seconds?
Yes, in arc seconds, it depends on the arc seconds per pixel that your camera is.
Right.
And I'm using an 800 by 600 part of the camera. It even goes better than that, but I've forgotten now exactly. And 800 by 600 with that sensor, I think we're into an arc, half of an arc minute to an arc minute. But if you go to full resolution, which causes the solve to take longer, you can get it down into, I think the best you can get is probably 20 arc degrees, I think is about what it was, or 10 or so. But you can put a more telephoto lens on that and get, so it all depends on what your pixels per arc second are, or arc seconds per pixel are.
Okay, I have another question. What catalog are you using for this?
The plate solver itself is called Astrometry, and you'll have to go off to it now because I've forgotten. It's been so long, but it uses the I can't remember. I don't know if anyone else can remember.
I happen to know the answer. It's Tycho 2.
There you go.
What is it?
Tycho 2.
Tycho 2.
Tycho 2, okay.
It can use it. I don't think I have loaded Tycho 2 because it's bigger than the one that's on it. But you can actually go off and load any one from where's it called again? Astrometry. And they have several catalogs. You can actually load them on to the Sky Safari. It's just a Raspberry Pi. And if you're computer literate enough, you can get those loaded onto it.
So you read all the interfacing software and everything, Dale?
Yeah, sort of, yes. I saw a guy on Cloudy Nights who was already doing it using Astrometry because I'd never heard of it. And as a matter of fact, it was Mel who talked about plate solving. I'd never heard of that about 3 or 4 years ago. And he was talking about how it'd be nice to have plate solver out in the field, and started thinking about, once I learned what plate solving was. And then this guy on Cloudy Nights had it with a different camera, but was using Astrometry. And he had a routine that allowed it to talk to Sky Safari to give it coordinates. And so I took that routine and I rewrote it a little bit in Python, and I rewrote all the browser information and its link to Astrometry that's running on Raspberry Pi. That's all written in Python as well.
Good job.
And then I got tips from Mel on how to write a browser interface. I had never realized a browser interface could look like a computer. And with his help, he mentored me a little bit, and watching his web pages, I discovered how to use JavaScript to create the interface.
Really nice work.
Yeah, I'd like to add, Dale, that and I mentioned this on the OSW list, I think, is that one of the side benefits of your system is that the camera lens never dews over.
Yeah, you're the first tester of that.
Yeah,
Have plenty of
well,
dewy skies, but my skies have been all full of Canadian smoke.
yeah. Well,
Can you fix that?
yeah, just for everyone else's benefit. I mean, I had this out on a night about a little over a week ago, and the humidity was off the charts. I mean, everything was drenched. I mean, my hair was wet in like 5 minutes. I mean, it was just, if it could have been over 100% humidity, it was. And I was out for about 4.5 hours, and everything is like I just poured water all over everything with the hose, except for the SkySolve camera. Dry as a bone. So the heat from the Raspberry Pi,
Why was it dry?
the heat from the Raspberry Pi kept it warm enough
Oh,
not
that's
to.
good.
How
Yeah.
many
Right.
watts?
Sorry, go ahead.
It's a lot of watts for what it is. It draws about, when it's trying to solve, it draws about 1 amp at 5 volts. So there we go. That's 5 watts.
Which is why you don't want the camera
No,
located under the incoming lighting
Yeah.
from the sky.
no, you
Yeah,
like
yeah,
it,
have it towards the top of your telescope. Yes.
right.
Any more questions here or out in Zoom? Okay, thank you, Dale.
You're welcome. I'm signing off.
Thanks,
So
Dale.
I do have a question, Dale, if you're
Okay.
still there.
I am.
Do you see, or do you plan to make a version of this that you could use on a go-to telescope?
Well, this can be used on a go-to telescope, but it's not the telescope. So Sky Safari has to, if you've got a go-to telescope, you want Sky Safari to tell it to move. So on Sky Safari, it's either got to talk to this or the telescope.
Oh, okay. So you, instead of selecting a push-to telescope, you'd select a go-to telescope in Sky Safari.
Well, you can't, because then it can't talk to this. So
Oh,
then it can only talk to one telescope, I think, at a time. But you could have two, let's see, I was going to say you could have 2 Sky Safaris, but one can't talk to the other. And so, but, so
'cause
yeah,
I know
it can
I
be
was thinking
go-to,
about this.
but you could do it. I have, of course, Argo Navis and a Servo Cat. And so it could be, this could be mounted, and this could be talking to Sky Safari, and the Argo Navis could tell the telescope where to go to. So, but you don't really need to do that once you already know where it is. Of course, it's nice to have tracking that the go-to telescope usually gives you.
Okay. All right. No, Rob has a
I
question.
just have an observation. I haven't tried your stuff yet, but I totally want to. I have tried Celestron's cell phone thing. What do they call it? I forget.
Intelligence and Star Sense or Intelligence. There's 2 companies that make that now.
Let's call it No Sense and in Intella, I don't know what, but they don't work. Dale, you've completely killed the competition as far as quality is concerned. These guys, there was a guy up at our Stubbs Stewart State Park in last New Moon, and he had this Celestron product on his 10-inch Dob, and he's like, I want to find the Ring Nebula, and so he moves over to the Ring Nebula, and it's like we look through his Telrad, which is perfectly aligned, by the way, and he wasn't even in Lyra. So I asked him to show me how you go through the alignment and calibration of this thing, and it was damn near impossible to do. And one of the key features that was missing, it just was like intuitive to me. I said, well, you're pointing at this star, I can see it. We pointed it over to I think Arcturus. Like, they're not Arcturus. There was Arcturus on the screen. Now tell it you're pointing at Arcturus. It couldn't even do that, which I think is a key feature of what you've got. You can tell it what it's looking at, right?
Yeah.
Yeah. Okay.
Yeah, through Sky Safari.
Right. So just an observation that Dale, boy, you've really cracked a nut on this, and I don't know why these other guys haven't.
What I liked about it was the fact that you don't have to know the star names and be on the right star. I quite frequently on my Argo Navis and Servocat, I picked what I thought was the right star and it wasn't. And then I go, oh crud, then I've got to resync the whole thing. It's a pain in the neck to get that all set up. And this one, it just looks at the sky and says, oh, there's where you are.
Yes.
Okay. More comments? No? Okay, another round of applause. There we go.
All right, thank you.
Very good.
And I see Ed had a bunch of snow. We have snow flurries coming down now. So it's headed towards us, but we're not supposed to get any on the ground.
Well, okay. Well, good luck with that. We had frost today. That's about it. Okay, so we're going to, let's see, we'll start just a few minutes early. This is the final presentation of today. It's the Peter Abraham's Astronomical History Talk. Now, Peter was a longtime friend of some of us here. He's from the Portland area. He was a longtime member of the Rose City Astronomers, and he was very interested in the history of astronomy, antique telescopes. And every year at the workshop for, I don't know, maybe 8 or 9 years, he would give a talk about some aspect of the history of astronomy or the history of some type of telescope technology. And it was always fascinating because it gave us, you know, some idea of where this has all come from. And so he passed away a few years ago. But in his memory, we try to have this talk every year. Sometimes we can't find somebody who has a topic or who's willing to present. But this year we do have a presentation I'm very much looking forward to, and it's a PowerPoint that is narrated. So I'm going to try to bring this up. And
thank you, Howard, for running it. I hope the sound will come out well for everybody in the pre-recording, but I can usually be more articulate pre-recording these things. So let it rip, and I'll be here to answer questions at the end.
Okay. All right, here we go.
Hello, this is John Briggs speaking from New Mexico. And this is the Peter Abraham's Memorial History Lecture at the Eltasmuth Workshop in 2023. And my title is Anguish at Yerkes, the hitherto untold story of the early grave concerns over the 40-inch objective. First, I'll just say I'm very proud to be here thinking of Peter. He was a close friend of mine. He was very active with the Antique Telescope Society. And this is one picture I have of Peter when we were visiting the MMT telescope in Arizona. Peter was an amazing historian related to the history of the telescope. He collected a vast amount of information, and upon his passing, I'm proud to say that his daughter, Katie, turned over some 50 boxes of Peter's files and papers that we now have preserved at the Astronomical Lyceum in Magdalena, New Mexico. It's an incredible archive related to history of telescopes and history of optics. Many of us here are telescope makers. In my young days, I built this observatory in Massachusetts, starting with a 14-foot diameter silo top. I did it all by myself. I describe it as the great project of my youth. Here's my friend Joe Zajac, who went on to become an engineer at Harvard Smithsonian. and still is working there to this day. The observatory housed this 8 3/4 inch refractor that, believe it or not, had been given to me. I heard about it, I tracked it down, I found it as a pile of parts at a school in Western Massachusetts, and I refurbished it and was able to assemble it and house it as you see here. It had been made by Robert Lundeen and Associates in the early 1930s, but it had been used only briefly before being put into storage for some 50 years. Fortunately, all the parts survived. It wasn't very hard reassembling them. I had great fun refinishing the instrument and painting it red, and a great joy using it for some years in this observatory, housing it. And it only reinforced my interest in all telescopes, and particularly refractors. But our subject today is Yerkes Observatory, and this is my favorite historical picture of Yerkes. There's a house on the immediate right through the trees there. You see just a bit of it. That's the house that Edward Barnard built and lived in from the earliest days of Yerkes Observatory. The farmhouse in the far distance is where William Morgan, the stellar spectroscopist, lived. Yeah, when I started reading about places like Yerkes and seeing old pictures like this, these black and white pictures, it was almost, to me, an image like this, the place was like a dream. Hard to imagine the reality of a place like this. As I was learning about these things around the time I built that observatory and thinking back about the history, images like this were kind of mysterious and, of course, amazingly appealing, making you really want to go there and see it with one's own eyes. But to this day, it is very much a real place. It's not just a black and white historical dream. It's a beautiful and colorful place, and amazing to see. The detail in the building is spectacular. The inside also absolutely spectacular. And even for all the astronomy and astrophysics progress that was made at Yerkes since its dedication in 1897, what I'm afraid it's of course famous for is the giant 40-inch refractor. And what we want to talk about today is some of the history, a bit of which has remained obscure to this day. So let's set the stage by looking back at some of the classic construction photos from the earliest days of Yerkes. The dome is 90 feet in diameter. It was built by Warner and Swayze, and of course, there's a figure there to dramatizing the size of everything. And back then, men were men, iron was heavy, and pulleys worked really well. How quickly we can click through these slides, only trying to imagine the labor involved moving the iron castings and getting them into place and assembling this and the entire building. Check out the ladder in the background on the right-hand side. Up you go, workmen, to get something done. It's, of course, just impossible to imagine the labor involved to accomplish something like this, let alone the design and the instrument making that went into creating all this. Absolutely amazing. Maybe many of you have seen these images, but there are going to be some that I bet none of you have seen. This assembled telescope tube is about 63 feet long. And here it is in a picture that was reproduced in so many 20th century astronomy textbooks, successfully assembled, in fact, operating in its glory days. But, you know, along the way, there were various setbacks, and they overcame them all. And really, this presentation is about some of those setbacks, not all of which they took the time to talk much about in their determination to overcome them and continue successfully making progress, as they certainly did. It was indeed a successful engineering marvel. The elevating floor is a wonderful feature. The eyepiece end of the telescope, of course, swings through a gigantic arc. This is no L-Smith telescope, but it's a great convenience having this elevating floor. And the founding director's father, William Hale, was an elevator engineer. And George Ellery Hale, the young man director, can you imagine being director of this when you're only about 27 years old? That's how old Hale was, if I remember right, as Yerkes started under his leadership. What a place. The elevating floor was great. And here it is at its topmost position, and notice the telescope is looking at the North Celestial Pole here, but nevertheless, the eyepiece end, in this case with the spectrograph attached to it, clears the floor, so you can do a German flip with the telescope, even when the floor is all the way up, and you won't necessarily bump into anything. But something terrible happened the morning of May 29th, 1897. We can imagine it was a beautiful spring morning. The telescope had been in use the previous night up until about 10 p.m. The adjustments to the instrument had been ongoing, but this was all before the dedication of the observatory. They were anticipating that to happen soon, but given what happened, it had to be delayed. So I'm going to read from a handwritten report by George Ellery Hale himself about what went down. Sound heard about 6:45 a.m. by McKee, who came to observatory and tried to get in. He is positive that no one was in the building. Sound heard by Mrs. Hale, Mrs. Wadsworth, and servant. McKee called Dodge, and Mrs. Hale awakened me, and I came at once and saw the floor before anyone had entered the building. Climbed up on dome, could see no injury to objective. Myers reached powerhouse about 7:15, no power on before. I sent Dodge for Elliman about 7:10. The latter came up at once. Here you go.
Oh.
Dodge heard the crash, looked at his watch and saw it was 6:43. Heard two crashes, a loud report followed by a lesser one, duller, about a second later. Looked at powerhouse chimney and saw no smoke, thought perhaps someone was closing the dome, but saw that no one was there. Then McKee came over to the house. Of course, the concern was what might have happened to the objective with the collapse of the floor. And there's a story that it took them some time, some considerable time, to really access the telescope easily again. And it had been quite an interval. And when somebody looked up through the tube, they were horrified because it looked like maybe there was a network of cracks in the lens. But it turned out it was a spider's web, and the lens was in fact okay, thank goodness. But Hale, in the report of the morning of the accident, added, Mr. Lawrence informs me that Mr. Carpenter of Williams Bay says he saw the cable connections made and thought them insecure. There had been worries that maybe the telescope and the project had been sabotaged. Even so many people disliked Charles T. Yerkes, who had made the donation and was becoming all the more famous as the observatory was being built. But that was not the case. It was simply that the cable clamps had given way, and it was a setback, but they overcame it. One can imagine how it taxed the nerves, especially people like George Ellery Hale, who seems to have been fairly high-strung by nature. But they overcame this, and of course, Yerkes carried on very successfully, but not without other setbacks. Hale himself was especially interested in the sun, and there was a portion of the Yerkes rooftop that rolled away, exposing the inside to skylight and sunlight, and the associated room that ran between the two smaller domes was called the heliostat room. So the idea was to capture a sunbeam with a heliostat or coelostat from this roll-off roof area, and then shoot the beam horizontally down some long focus instrument and long focal length spectrograph. But here we see what I believe might have been the Ritchie 24-inch mirror set up in a temporary tube assembly in the roll-off roof area. What they found, however, was that this observatory for the sun was really not too good, because the masonry heated up fast in the daytime sunlight, and the seeing was disappointing from the heliostat room. Would have been the heat rising off the gargoyle there facing towards the east. And in the elaborate basement machine shop area, they were building the solar apparatus, the coelostat mirror mounting here, and on the left-hand side, a mounting for a 24-inch diameter paraboloidal, long focus paraboloidal mirror for this horizontal telescope. And when the heliostat room was disappointing in the main building, they elected to set up the solar apparatus out on the lawn in a wooded building, but where they believed they would have better daytime seeing. All this was going on in the very earliest days of the observatory, and what must have been a dizzying pace of effort and activity is hard to imagine. But they were all young people, mainly young men, and they were throwing themselves at this with all imaginable passion. And there's the completed solar observatory on the south lawn. And that's actually Lake Geneva behind the trees, some distance down a hillside. but really close at hand. But oh no, this is what happened. Evidently, before they had a chance to accomplish anything with the observatory, something went terribly wrong. It caught on fire and just wiped it out. Whether it was an electrical fire from, say, a spark source in an arc spectrograph, I don't know. Or whether it was something to do with a bright sunbeam, even at F30, which I suspect the telescope was operating at, because that's the focal ratio of the snow at Mount Wilson. Even an F30 solar beam is bright enough to set some things on fire, but this day, it looks kind of like a cloudy day, but it is not recorded, at least in anything I've ever seen, exactly what the cause of this fire was. But in any case, what a loss.
Oh.
Imagine the discouragement after having figured the 30-inch optical flat that you see here destroyed by the fire. But notice the iron parts are actually not destroyed. The governor mechanism on the extreme left looks more or less melted or something, but the iron survived. And so the instrument subsequently arose phoenix-like after this fire. They had to remake a lot of parts, and evidently all the optics, but the iron parts, as far as I can tell, were reused. Undaunted, they proceeded along and they built it up again and built it bigger and better than ever. This was actually the first snow telescope housing. Mrs. Helen Snow came along and funded the project, and she and her family lived there on Lake Geneva, and the telescope was actually named as a memorial to Mrs. Snow's father, and it was set up with new optics quite magnificently. And here, showing just a small part of the gigantic long building, you see a scientific meeting. George Ellery Hale is actually in the group there. I'm going to count in from the left, going in. 1, 2, 3, 4, 5, 6. He's the 6th person present. He's sort of standing in back with his head tilted a little bit, but he was merely in his late 20s and in charge of all this. What tremendous activity. You see, that's the roll-off roof part of the structure immediately above the group, but it was a tremendous building there in the grounds of Yerkes Observatory. But interestingly, it did not last there long, as I'm sure many of you know, because George Ellery Hale persuaded Mrs. Snow to allow him to take the instrument and set it up on Mount Wilson as a solar expedition by Yerkes Observatory. And it turned out that the Snow telescope never came back to Mount Wilson. It's still there as the first major instrument at Mount Wilson, and I've actually used it there myself and for education projects. And but just to imagine thinking of what this thing went through, given its history, and imagine the perseverance of the folks involved, ultimately succeeding. But this talk is really about the 40-inch objective itself. And most of what I've shared is well known to a lot of folks. But I'm going to get into some stuff that is less well known. But many of us grew up reading in textbooks that the 40-inch lens would likely never be exceeded in size because it was optically impractical to build a telescope lens that was larger. Well, shown here with the 40 inch is a friend of mine, Dr. Steve Tomczyk. And Steve is a solar physicist, and he specializes in coronagraphs. And thinking deeply about coronagraphs and wishing he had access to an ever larger one, Steve came to the realization that a 60-inch refractor would be an appropriate step forward nowadays for a modern coronagraph, thus greatly breaking the record in size for a refracting telescope. So Steve works for High Altitude Observatory in Colorado. And although many of us have read for various reasons, and the authorities argued in the textbooks that we grew up with, that a lens simply flexing under its own weight would destroy its optical performance. And for that reason and other reasons, you simply could not build something bigger than the 40 inch. Well, Steve and his colleagues thought about it, and they realized that that was simply wrong. And there were historical astronomers and telescope makers who recognized that the conventional wisdom was wrong. Among them was pioneering solar physicist Charles Young, who pointed out that when a lens deforms under its own weight, the changing shape of the front surface is compensated by the changing shape of the rear surface. So gravitational deflection doesn't really affect a lens as much as some people thought. Also, Elvin Graham Clark, the son of Elvin Clark, he recognized this too, and he, before he died, wrote something that indicated he saw no limit in making larger lenses, but not everybody appreciated what Young and Clark knew. But Tomczyk did, but he decided he had to know everything he could about the Yerkes lens to argue for his proposed 60-inch coronagraph. And that's why he wanted access to the 40-inch to study it, and I assisted him in that process. Now, you might have noticed the lens was pretty dirty with Steve standing beside it there. And one of the reasons it gets dirty all too fast is there is a shutter mechanism to cover the objective that's a lot like a roll-up window shade. And this was added to the telescope, of course, in the 20th century. It's powered by a motor. And you can see how dirty the forward surface of the roll-away shutter gets. But of course, when the front surface rolls up in the top of the blue box there, the front surface becomes in direct contact with what is subsequently the rear surface of the cloth. And so I fear the dirt on the front is transmitted to the rear surface and then shakes off the shutter and falls directly on the lens. So this is really not the best lens cover design at all, but that's, I'm afraid, what they've had at Yerkes for a long time. Now I'm just going to lead you through some of the steps that we took back. It was in 2009, if I remember right, to understand some technical details of the 40-inch. Here, Steve is mounting a laser that's going to point towards the front end of the tube to measure its flexure. The tube actually flexes a lot, and I won't get into all that, but we tried to measure all kinds of things about the telescope and also its optical design, because surprisingly, there were issues even into contemporary times of a certain lack of knowledge, confident knowledge regarding the optical details of the 40-inch. It's really quite surprising. And Steve was determined to nail all of this down. It's interesting how the front of the telescope tube has a variety of vents. Most big Warner and Swayze telescopes do have air vents to let warm air out, to chimney out from the front of a refractor telescope tube. And there are two of them on the 40-inch. One is slit, you can see the hatch slit open, but that's also a big enough opening that you can reach in if you need to clean the back of the 40-inch objective. Now, in the optical design used by the Clark family for their big lenses, there was a significant distance between the crown and flint elements. In the case of the 40-inch, that distance is over 10 inches. And consequently, the cells were usually designed with a sliding ring that could close or open air ports on the circumference of the cell. In the case of the 40-inch, the sliding collar was a bit corroded, and it was not practical to just slide it open to expose the many apertures around the circumference. So we simply undid some screws to let the collar just fall away, as you see it here, allowing those oval apertures to be accessed to the space in between the lens elements, which is convenient for cleaning, but maybe even more important for thermal equilibrium. If you really want to get the best performance out of the telescope, you've got to let that lens cool down to ambient nighttime temperatures. That's what these ports especially were for. Now, you could stick a camera up inside the tube and look out from the back of the objective through it at the catwalk and the open doorway. And of course, you see how filthy the objective had become when Steve and I visited Yerkes. I was no longer based at Yerkes when this work went down. I've been employed there for 15 years, but I was teaching in New England by the time this collaboration happened in 2009. But I always loved the chance to get back to Yerkes and maybe to have a chance to clean the lens too. Now, I bet some of you know that there was a crack in the crown element of the Yerkes lens. And they had to stop that crack when they discovered it circa 1980, or maybe it was the late 1970s. I can't remember for sure just when it was. They drilled a hole through the crown element about 3/4 of an inch in from the edge, and you can actually see the hole. It's about 1/2 inch or maybe 3/8 of an inch, something like that, in diameter. And it's near the bottom center of this image. They drilled that hole. A glass expert came and drilled the hole to stop the crack and make it very unlikely that the crack would propagate along. And this was reported in a news note in SkySolve magazine, again, circa 1980. Of course, this would have been noticed with considerable alarm, but they dealt with it. So here we are looking in at the crown element, and you can see how the glass is secured in itself with these blocks. There are 3 of them on the front side of the crown, and similar blocks that are shaped in a more triangular fashion, at least as they're bolted to the inside of the cell, all similarly secure the flint element, and the cell comes apart in 2 parts. But you can see some of that in this image, of course. But of course, imagine the alarm when you have the world's largest successful refracting telescope and you discover there's a crack in it. They were able to address this issue and it wasn't a worry anymore. Wow. This documents how filthy the lens had become in 2009. Yeah, 2009 when we visited. And this is looking at the bottom front of the objective where moisture would gather, dew, etc., the inside of the cell. And by the way, I only heard a few days ago something I didn't know until recently, that the 26-inch lens at the University of Virginia, an earlier Clark from the 1870s at Leander McCormick Observatory, that developed a crack that was recently also stopped with a drill hole. So this is something that can happen to larger objective lenses. Also, I'll just point out there's a hole that's been drilled through the cell, that dark spot there where the water congregates. The telescope is always stored in the same position. Water gathers in that spot from dew or whatever, but there's a hole through the cell to allow the moisture to drain out. It's better to have it on the outside of the cell than the inside of the cell if you're going to have water on your 40-inch objective. You cannot always have the luxury of a full disassembly of a lens to clean it. That is usually appropriate. But in the case of the 40-inch, the idea is to buy many, many, many inexpensive new cotton towels. And although this shot is jumping far ahead in the process, the idea is to wet the towels with soapy water and merely apply them in gentle contact with no rubbing to the lens surfaces, and using enough towels, the filth will eventually be absorbed into the cloth, into the cotton fibers, and you can get rid of what we've seen in the earlier images. And then only finally, by ongoing dabbing and moving away from soapy water to distilled water and ultimately to alcohol, with very gentle dabbing and an absolute minimum of rubbing, you can clean up a lens. Along the way, once a towel has been in contact with the lens, you essentially discard it, and you have a large inventory of fresh towels to continue the process very slowly, so that you are not inclined to be rubbing inappropriately a filthy lens. The last thing you want to do, and to have an awful lot of distilled water and alcohol available for the process. Eventually, a clean lens. Not perfectly clean, because you're not striving for perfection. That's when you might injure it, but certainly one heck of a lot cleaner than it was before. And now, photographing through the lens with the camera handheld inside the tube, you can see the view is much, much better than it was before. With the lens satisfactorily clean, it was possible for us to use a digital spherometer to measure all four of its surfaces, because surprisingly, even after all these years, there was some considerable uncertainty whether the recorded radii of curvature were accurate, especially for the rear surface of the flint. And I much regret that I cannot remember the name of the member of the Amateur Telescope Makers of Boston from whom we had borrowed this excellent digital spherometer for this project. Here again is a shot of one of the three blocks that secure the crown element in the cell. Looking through the crown on the right-hand side, you can see one of the larger blocks securing the flint inside the back of the cell. This will be relevant in what I'm finally going to get at showing you. Interestingly, the inside of these blocks has an aluminum surface. Similarly, there is an aluminum surface behind the crown element in the same spot, so that the lens is resting on relatively soft aluminum pads in three spots. And just to give you a sense of scale, in some of these close-up photographs, here's a mini mag light with two AA batteries in the field of view just inside the front edge of the cell. Here's a clearer shot of the larger triangular blocks that secure the flint. And you are actually looking through the flint to the left of that block, and you see a dark rim that's on the back inside of the cell. It doesn't look like shiny aluminum, but according to the documentation, that is actually an aluminum surface allowing the flint to be essentially in three-point suspension. It's not really a point, it's a rim there. But that's how the elements are secured in the Yerkes cell. Now, Steve and his colleagues at High Altitude Observatory have described this work professionally in support of their coronagraph project, which is called the Cosmo project. And that's worth Googling about because the site survey for the 60-inch refractor is underway right now. But at a meeting of the Hartness House workshop some years back, Steve visited the Stellophane convention, and where we have the Hartness House workshop, and we shared the presentation of this PowerPoint. He put me as the first author, but really Steve and his engineer colleague Peter Nelson, they were the ones who really did the technical analysis that's reported in this presentation. I'm going to go through a little bit of it. The Yerkes objective, debunking the myth of the large refractor limit. Typical of the conventional wisdom that many of us grew up with, we'll quote a couple of them. The big 40-inch glass at the Yerkes Observatory appears to be the maximum development in this direction. Lenses larger than 3 feet and a half in diameter, even if they could be cast and figured successfully, would probably produce internal strains by their own weight, sufficient to ruin their optical qualities. And even Henry King in History of the Telescope wrote, "We can say with certainty that 40 inches is the limit for the useful size of a refractor. A larger glass, by reason of the increase in lens thickness and surface area, would probably absorb and reflect all, if not more than, the extra light received by the increase in aperture. In addition, the cost and difficulty in obtaining suitable discs and compensating for their reflector would present a great, if not insuperable problems." And there were more examples of recent conventional wisdom. I won't go through them all, but you could pause and look at this in the recording. As Steve and I made these measurements, it was surprising how many mysteries remained of the Yerkes example. The indices of refraction had been unknown to Elvin Graham Clark and his Chief Assistant Carl Lundin. In 1928, they were finally measured by the National Bureau of Standards and published by a Yerkes astronomer. The radii of the lenses were poorly measured, and there was contradictory information about them. The lens rotation appeared to change image quality if you rotated one element relative to another, as had sometimes been done a bit. There was concern about possible lens flexure, and there was concern about the 3-point suspension as the lenses were supported in the cell, as I showed you with the pictures of those pads and things. There had been serious concern about the mounting of the lens, and none other than George Ritchie, who figured the optics at Mount Wilson, wrote a letter to Carl Lundin at the Clark Corporation in 1903. Ritchie said, quote, "We think," he was then at Yerkes, beginning the grinding of the 60-inch mirror at Yerkes that ended up at Mount Wilson. Ritchie wrote, quote, "We think it would be desirable to introduce additional supports, arcs carried on levers for both lenses, so that each lens will rest on 9 or 12 arcs instead of 3. An additional reason for doing this is that there appears to be a slight triangularity of the images given by the objective." Now, there was, in fact, a much more profound concern over a problem that drove these comments, which has never been discussed or published before. For whatever reason, the more advanced support of the Yerkes lens elements was never executed. There were measurements, early measurements of the performance of the lens by people like Philip Fox. And in the papers today, people have been talking about the Hartmann test, and the German astronomer who had invented this optical test was advocating in 1908 that it be applied to the 40-inch, and Fox indeed did that. And what Steve and I did was to repeat the Hartmann test as an optical assessment of the 40-inch. And I'm not going to belabor it, but the idea is to put a mask in front of the telescope so that starlight enters the tube assembly only in well-defined small spots. And then you can put a photographic plate, or nowadays CCD detector, actually out of focus behind the image plane, and record the spots and measure them astrometrically. And one can thus do some basic ray tracing and understand how tightly together the beams of light must be passing at the focal point. It's a great way to observationally measure the optical performance of a telescope. Hartmann suggested a formula to quantify how sharply a lens focuses, and a single constant that he labeled T would quantify the performance of an instrument after this Hartmann test was performed. I won't go through it all here, but T, this value T that you come up with after the measurement, is approximately equal to the image size in arc seconds. An excellent description of Hartmann test in English is in volume 1 of the publications of Van Vleck Observatory at Wesleyan University. So Steve's investigation that was reported in 2009, and I'm borrowing slides from our report at the Hartness House workshop, he summarized it describing we measured the curvature of the surfaces with a spherometer and the separation of the lenses. We fabricated a Hartmann screen and mounted it on the Yerkes 40-inch, and we observed Vega on the night of August 26th from 10 p.m. to 4 a.m. The idea was the optical performance of the telescope changing as the gravity vector changed on the lens over these 6 hours? Here's what the Hartmann screen looked like mounted in front of the lens. 176 apertures, each of them only a little over an inch in diameter. Here's one of the resulting images of Vega out of focus. There's a lot of diffraction structure in this pattern, but the actual images directly from the apertures have circles around them, 176 circles. This slide shows the deviations from the ideal grid pattern, and it was not a simple pattern. So something complex was going on with the image structure. It was not this suggesting the starlight is not being perfectly focused. So here are the results from the Hartmann test. You can think of this as an observational ray trace of a working telescope, and the image in the very center is showing the best focus. It's labeled 0 there, and the star image is slightly triangular. But on the other hand, my recollection is the units in these graphs are arc seconds. So the triangularity there is on the order of a little bit less than 2/10 of an arc second. And the diffraction limit of the 40-inch is around 1.2 of an arc second. So it was very close to diffraction limited, but the star images were slightly triangular in perfect seeing, and that is exactly what early observers reported. And for each measurement of the best focus, this constant T could be calculated, and at the best focus, the minimum value of T was about 0.2. And that, according to Hartmann, who invented the test, made for a very, very good lens, but not necessarily absolutely perfect. But this here was particularly the result that Steve Tomczyk was looking for. How did T change as the telescope tracked Vega for 6 hours? And there was essentially no change of its optical performance. T is plotted here as a function of zenith distance, and it's riding right along there, more or less constant. There are some outliers a little bit higher than 0.2. So if a lens were changing its figure dramatically as a function of its gravity vector, you'd see T change, and it's not changing. And Steve took this as strong support for why, in fact, as he expected, he and his engineers at High Altitude Observatory understood and anticipated that a 60-inch lens would work just fine. And the conclusions of the study: the Yerkes lens does not deform with changing gravity vector, which was consistent with the finite element analysis at High Altitude Observatory. This is in conflict with the early study of Philip Fox. The lens was aspherized by Clark and Lundeen when it was made. The lens is not quite diffraction limited. It's limited by figuring errors or more likely refractive index variations in the glass. But it's still a pretty darn good lens for its size and its era. So finally now, after all this presentation, I'm going to get to the bit about the anguish. And so here we have another image of the crown element, the edge of the crown element looking in from the front of the cell, the front of the telescope. And on the back inside surface of the crown glass, in an area that's actually in contact with one of those support pads that we now know were made out of aluminum, it looks like there's some bubbles there or something. They're not bubbles actually, but they are spots where glass has been ground away. The glass was ground away to stop cracks. Both the crown and flint elements in 1903 were noticed by Yerkes astronomers to have many cracks impinging upon the elements. And it was George Ritchie himself, who was then on the staff of Yerkes, wrote to Carl Lundin at Elvin Clark and Sons Corporation. Elvin Graham Clark had died the same year Yerkes was dedicated, 1897, but this is October 8th, 1903, and this is what has never been published. Ritchie wrote, "Dear Sir, I was much surprised a few weeks ago to find in the edge of the flint lens of the 40-inch a chip about 1/4 of an inch deep and 1 inch long, which occurred where the glass rests upon one of its 3 support arcs. The chip is at the edge on the inner surface. The silver or aluminum surface of the supporting arc had oxidized badly, thus making a raised point in the supporting surface, and the glass had apparently become cemented to it." This is what Ritchie at least was speculating had happened. "As the lens shifted in itself, this had evidently caused the chipping at the edge. On careful examination, I found that the flint lens was chipped slightly at 2 other arcs of support also, but less badly and in a different way. The chips not having broken out, but showing slight cracks on the inner surface about 1/4 of an inch from the edge. These cracks invariably occur where oxidation of the supporting surface had taken place. We took the cell from the tube and removed both lenses and found that the crown lens was also affected at all 3 of its supporting arcs, but in a different manner still. Where oxidation of the metal and arcs had taken place, flaking or scaling of the glass had started. None of these flakes or scales had been entirely detached. However, chemical action had apparently taken place between the metal surface and the glass, as the polish of the glass had been entirely destroyed in the spots where it had been in contact with the oxidized metal surface." Here's another shot showing more of the ground out places, because that's what happened. Ultimately, Mr. Lundin had to return to Yerkes, and the lens was taken apart, and at all spots where these cracks were appearing, he went in and he ground away the glass to stop the propagation of the cracks. Ritchie wrote onward, "We washed lenses carefully and put them back with 1 thickness of writing paper between the glass and metal at the supporting arcs. There has apparently been no further cracking since this was done. We think it would be desirable to introduce additional supports, arcs carried on levers for both lenses, so that each lens will rest on 9 or 12 arcs instead of 3. And interestingly, though, that was never done. Maybe some of the other complications, like the burning of the solar telescope and the deadline to rebuild that Phoenix and get it out to Mount Wilson, backburnered the idea of building additional support into the cell of the 40-inch. I don't know. Here's another shot. I think this one is showing work on the inner flint element, given we see the open aperture on the lower left. So I think I'm photographing through the crown and trying to focus as best I can on the flint element deeper inside the cell. But surely there must have been anguish when they noticed this going on. You know, when you've got the largest refractor in the world and you've built that enormous cathedral of an observatory to house it, you don't want the lens cracking circumferentially in towards the edge. Shortly afterwards, Hale himself wrote to Lundin, and he said, "Dear Mr. Lundin, Mr. Ritchie has already written you regarding the small cracks which appeared in the 40-inch objective at the points of support. We have had the objective out of the cell again today, and there appears to be some evidence of the existence of one small crack in addition to those previously seen. This is on the very edge of the disc and apparently could only be produced by the weight of the glass when the telescope is standing in a nearly horizontal position with this edge down. Mr. Ritchie thinks there is no danger that the cracks will spread, but as I wish to take no chances, I hope you can arrange to cut them out for us very soon. I understand that you are coming west sometime in November, and I trust that you will arrange to do this work while on that trip. I, of course, greatly prefer to have you undertake it rather than anyone else. We are building a support system for the objective, which will prevent such difficulties in the future. Today, we rotated both lenses in the cell through an arc of 60 degrees. Hoping that you will be here very soon, I am very truly yours, George Ellery Hale." Of course, the additional support was never built, and the telescope has survived, as you see it here. And there was a statement by Mr. Lundin, and I'll conclude by reading that. In March 1904, he had visited, and it is regarding condition of 40-inch crown and flint lenses. On removal from cell, 7 places were found where the crown glass was cracked around the edge, and 11 places in the flint glass. These were all ground out with a circular cutter and the entire crack being removed. The cause of these cracks is not definitely known, except that some of them were due to chemical action between the glass and the aluminum bearings. It is recommended as a precaution against their reappearance that water shall be kept out so far as possible. The glasses were cleaned and replaced. So there you go. But I never heard about these cracks, even though I had worked at Yerkes for many years, until finally the director, Kyle Cudworth, passed to me a file that he had in storage somewhere that documented all of this. And I was rather amazed to read about all these cracks in the Yerkes lens that had never been discussed before. There's some bits of history, I guess, astronomers are very happy to forget about. This was one of them. Thank you very much for your attention today. I hope you found this interesting.
Well, my talk went a long time, and I'm speaking live now. And but if anybody cares to raise any questions, I only misspoke once or twice in the presentation, but in ways I don't think you'll notice. But here I am, but again, thank you for your attention, folks.
Yes, we do have some questions.
I have a question. My astronomy club said when you go, ask him if he would participate in a Zoom meeting at our club sometime next year early.
Sure, $5,000. No, actually, I'm a soft and easy touch. So, but hey, if you've got a check, feel free to send it. No, I'm teasing. I'm just glad to have this presentation done, and I'm a little slap happy right now, but that's not unusual. But by all means, if you would like another presentation sometime, feel free to email me or call me. My email address was flashed at the very end of the presentation that I gather is recorded, but anybody who has my email address should please feel free to forward it to anybody interested.
Thank you.
Your last comment about astronomers wanting to forget these things, that's the wrong attitude. And thank you for bringing this up and letting us know. Of course, modern glass shouldn't have these problems, and it's only through learning the hard way that modern glass has gotten as good as it is, enabling a 60-inch to happen. Is that 60-inch made?
No, not yet, but they are very serious about it. And as I mentioned, the site survey to locate it is underway right now. And one of the sites being considered is, heck, only maybe about 15 miles or so, or even 10 miles from my home, as a bird would fly, but would have to fly up pretty high. Magdalena Ridge is nearly 11,000 feet here in Magdalena, New Mexico, and it's south of my place. And so I am actually assisting the project right now, maintaining some of the more or less automated site survey instrumentation that has been installed by High Altitude Observatory up atop Magdalena Ridge. And of course, if this 60-inch coronagraph were to follow through and be located here, I'd just consider it incredibly cool. But it's and you can Google it. It's the Cosmo project, Cosmo, at High Altitude Observatory. And of course, my presentation was so long that I did dare say too much about it, and I'm not at all expert on it even. But Steve Tomczyk, who's the principal investigator, was actually a graduate student working on his PhD at Mount Wilson Observatory years ago, living there at the same time I lived there for a while when I worked as an observer with a 60-inch telescope. So our friendship goes way back, and it's just cool to see him working on this now. And he has received preliminary funding for technical development in the site survey. And it seems to me almost inevitable that the telescope will eventually be built somewhere, but it's basically taken his whole career to push it through to completion. But I'm optimistic we're going to see it one of these days. And it's going to be a single element lens made out of a fused silica with high ultraviolet transmission and beautiful, beautiful uniformity. And I think it's going to be about f10. But don't hold me to that, but check out the website.
Hey,
Go ahead.
hey, John, this is Dan.
Dan.
You mentioned in the talk that this was the largest successful refractor in the world. Can you tell us about the unsuccessful ones?
Yeah, I can try. And of course, it's subjective. If you talk to maybe a French historian of astronomy, he wouldn't want to describe the monstrous horizontal Paris refractor. But when Joe Ashbrook wrote about it in Sky and Telescope magazine some decades ago in his scrapbook history series, which was also republished very wonderfully into a book called The Astronomical Scrapbook, and I recommend to everybody that they get a copy of this book secondhand because it's great. But one of the chapters is entitled The Great Paris Telescope fiasco. It was something like a 49-inch, as I recall. It was a horizontal telescope. It was gargantuan, and it was fed by a single optical flat, gargantuan one in a very clever equatorially tracking mounting. And they even aspired to have two objectives for it, one corrected for visual work and the other corrected for photographic work. And there was some published science. Somebody made some drawings of the Ring Nebula with it, and there were some other things, but it was part of one of these exhibitions, like a centennial exhibition in Paris, and it was funded, but then it was not practical to keep it going and maintained. The objective apparently survives, at least the visual one, in the basement of Paris Observatory, but unfortunately the mechanical parts were evidently finally scrapped. But I refer you to our articles like Joe Ashbrook's that describe it, and there might have been some other large refractors that didn't quite get finished, and I forget the details. There was a Russian one, or there's the Howard Grubb in Dublin, Ireland, I think was trying to make like a 42-inch or something for the Russians, but I don't think that ever got fully off the ground. But I'll resist the temptation to go on and on with some of these things, because on this stuff I really can go on and on and on.
Okay, hey John, can you hear me?
Yeah.
Okay, this is Joe LaCour. When was the last time?
Oh, Joe.
Yeah, hey. When was the last time the objectives were out of the cell?
You know, Joe, I bet you those lenses have not been out of the Yerkes telescope since Lundin was there in, what was the year I mentioned? You know, what was it? 4 or 5, I can't remember. But I'll bet you anything they have not been decelled since Lundin's visit to grind out those cracks. And what I have learned in my experience, that although you have to be very careful doing it, it is definitely appropriate with even smaller objectives to occasionally decell them, so that you can clean the lenses really properly by tubbing them, and cleaning the cells. I've had several historic objectives in my possession where corrosion has occurred, even when the cell is made out of brass. The brass can corrode in between the cell and the glass. That takes up all the space. There's typically 3,000 or 4,000 clearance between glass and the cell, and you can feel it, man. You know all about it, I'm sure. You can the lens will rattle in a properly designed achromat, because thermal contraction will shrink the ring faster than the glass, and so therefore, in a situation where there's corrosion built up inside the cell and then it's cold, then there's pressure on the lens, and so go ahead.
Yeah, I can't think of anything worse than aluminum besides maybe magnesium to use. Okay, but
coming back then.
Well, wait. So when I mounted my lens, I have cork lining the cell and O-rings front and back, and that was based off of some experience we had with an underwater compass alignment. We used O-rings to align it, and testing was done, and it was extremely repeatable. So, but you model it, and you look at the load, and you select the appropriate O-ring. You contact Parker. I mean, you couldn't have you just don't touch it with the metal. I mean, I wouldn't get near the thing with metal. I mean, it's just too scary, like you said.
I would bet that all of that is lessons of history.
Right.
They didn't know that.
Yeah. But they had cork.
This is the value of its presentation.
They might have had cork, but they didn't have the Parker O-ring catalog. It's one I've used myself too. And the thing is, the
O-rings are nice because you get a lot of elastic averaging. Sheet rubber, you don't, but you could still use it.
Yeah,
because the O-rings Yeah,
The issue was that the old time astrometrists, especially when the Yerkes refractor really in an unexpected way proved to be an amazing workhorse, not just for visual microscopy that people like Barnard did, but for long focus photographic astrometry, for trigonometric parallaxes and things like that. And so the astrometrists were typically very shy to disturb a lens in any way when it was being used for a long, what's the word they used, a synoptic observational program. They, in fact, occasionally when lenses were disturbed and equipped with new cells because of corrosion, that's what happened at Swarthmore. Swarthmore, the 24-inch Brashear at Swarthmore got a new cell at one point over the case of its career. But then there was a systematic shift in some of their astrometric results. So that's one of the reasons the astronomers themselves were so shy about this and concerned about the dimensional stability of things.
Yeah,
so
and the O-rings solve the 3-point support problem because you get elastic averaging all over the place.
Right.
Now, it might not be that good for the astrometric stuff, but I don't know. You'd have to model it, stick it in the computer, see how much it moves. But it keeps it protected. If you bump the cell or something, or if something corrodes,
Sure.
And I would do everything I could to keep water off of it. That seems easy.
Yeah, it's just amazing.
Not being right next to a big lake.
Well,
I fear that I could tell stories about just my own observations of what happens at some of these big institutions. You would think that a place like Yerkes, over the many decades, there would be a certain very deep respect for the care and feeding, or so to speak, of something like the 40-inch. But there was, by a relatively tiny number of astronomers, but with the passage of time, there were so few still involved with the refractor, and they tended to be very shy because they were astrometrists and they were not necessarily engineers. And there are stories that I could tell about the neglect of things at many different places that are kind of horror stories. But we all know, these are the kind of the stories we swap at meetings of the Antique Telescope Society, and then we go have a drink. So
NASA let the Saturn V rot outside of Houston, and they realized they got to save this, then they got to restore it, and then they got to build a building to put it in. Same stuff. They just let this stuff go. I mean, you've been in more observatories than I, and it's just terrible.
It can be terrible, but yet there's hope. And I could go on and on about hope too. There are things happening that are really good news. There's something called the Alliance of Historic Observatories, which has just recently formed, and it has a lot to do with historic preservation and sharing information. And so there's good news as well as bad news. But I'm resisting. I'm trying to hold my tongue rather than go on forever here, though I'm happy with all your questions.
So it's really been 100 years since those lenses have been out of the cell. Is that what I'm?
That would be my very strong hunch. Of course, I didn't work at Yerkes 100 years. I only worked there 15. But there was a major refurbishment of the telescope in the 1960s. And something interesting might have happened to it then. But again, I kind of doubt it because of the conservative approach they would have had to the stability of the instrument, given the ongoing astrometric work.
Okay. That's scary. Yeah.
Yep, it is. Because you saw the pictures. When you look at all the filth, that's settled down in between the glass and the cell now. You know, it's not cool. So
Wow. Okay.
Any other comments?
Be careful with it. And if you need to take it out of the cell, I'm busy that day.
yeah, I'm getting older, and I'll leave that work to some younger enthusiast. I fear I've got enough other things to worry about now. Break my own lenses. So, but anyway, hey, how many folks are attending this live, wherever you are?
Oh, we have about a dozen people here.
That's nice. Well, thank you all for your attention.
Online,
Yeah. Yeah,
Got
about
14
20 online. So yeah, it was a pretty
Very
good
good.
crowd all the way around. Yeah. So thank you again, John.
Well, thank you. Peter was a really wonderful guy. Makes me proud to speak to you in this circumstance. And good night to all, and I look forward to staying in touch.
Okay, likewise. Good night.
Good night, John.
Okay, so this is the end of day one. I think we all had some very interesting times, learned some new things, and we'll start again tomorrow morning on Zoom at 9:25 a.m. Yeah. And again, for those who kept trying to get into the meeting 2 hours early today, please check your time zones. You know, if you're in a different time zone, please check the offset to the Pacific time zone. And if you are in the Pacific time zone, we're not going to start 2 hours early. So I'll just put that out because I get a ton of emails on my every time somebody logs in, and actually somebody even started the meeting several times. So don't do that either, because that generates a recording, and that'll have to go back and delete. So that said, I think we had a successful first day, and we'll see everyone again tomorrow. All right. Thank you so much.